here with us today. It's an important event, a scientific event, and I would like to open this event with some opening speeches of Mihai Brăslaș, the Vice Rector of our university. It's Thierry Marsano, the Head of Engine Calibration Department of Renault Technologie Romania. My colleague Pierre Podevan, as co-organizer, will send his message from Conservatoire National de Paris, and myself. I will tell some words in order for you to tell why are we here today. So, Professor Brăslaș, please tell us some of your thoughts.
First of all, I want to welcome you here on behalf of the rector of our university, Professor Tehnologie. Unfortunately, he could not attend this meeting because he was unexpectedly. But he wanted me to send his greetings to all the participants and to wish a warm welcome and success for this already traditional meeting. I use the term traditional because the cooperation between universities in the field of car industry is already establishing a tradition in our university, and this makes us very proud. We are living in the shadow of a giant, Dacia Renault, but at the same time, I'm very pleased to see guests here from Germany, from Austria, and from Italy. In a way, competitors in the same race, but competition based on scientific research. And this is, I think, what unites us all in the idea of making people's lives more comfortable and a little bit efficient, because engines move the world, and if we work together, make a contribution in the progress of building and exploiting engines, will surely bring benefits to many people, but at the same time, I do hope we will keep our planet still green for the years to come. If I come back to this important reunion, I cannot end without saying something I remembered about George Bernard Shaw. He used to say that those who can do, do. Those who cannot, teach. Our colleague, Adrian French, can do things and does things. He knows how to bring people together, how to strengthen friendship, and it is, we have to admit his important contribution to us being here. Once again, welcome, and let's have a successful meeting for our mutual benefits.
Thank you, Professor Brăslaș. Let me invite Thierry Marsano.
So, hello and good morning, everybody. On behalf of the Renault Powertrain Division, I'm very glad to be here with you today and to participate in this workshop. We have, since years and years, strong relationship with this university, with the Pitești University. we have often technical exchanges. We will introduce this year a very big training session about powertrain. This training session done together will be, I think, the new reference for this kind of training. And I think it's the first step for learning well. We welcome each year some students for internship, for 3 or 4 months for internships. That's very important for us. And we try to exchange, to bring some knowledge and some know-how when we can, and some equipment. So as you can see, this university is a key partner for us. We can see it changing, we can see it growing up, and to be able to organize this kind of event is the evidence that, this university change, evolves, and evolves in the right way. So congratulations to be able to do that, and good luck for the future. So regarding today's topic, we already work on this item, just a little bit, but we already work together on this item. When the first engine with this technology arrived in Pitești, at the university, we tried to bring again some know-how and some equipment to allow the university to use this engine. That's our contributions. And since then, dozens of students use this engine and were able to learn this technology. Other, but this one for sure. So regarding the technical issue, the variable valve actuation is for sure an interesting topic, because this technology became progressively, and in the same time that the CO2 pressure increased and the emission standards increased too, will help you to discover the potential and the target you can reach with this technology. So I wish you a pleasant day and a fruitful workshop.
Thank you, Thierry, for your kind words. And indeed, you helped us a lot. But you're going to see it in a few moments. I will invite my friend Pierre-Paul Devant as co-organizer who will tell you some words.
Ladies and gentlemen, dear colleagues, I'm giving the letter of congratulation of my colleague, Professor Georges Descombes, Director of our laboratory, addressed to the Rector of University, Rector of the University of Pitești, Lionel Guillet. This is in French and written in a small character, so I will not translate this letter. It will be boring, but I will underline some important points. First, I thank the University of Pitești to associate our institution the National Conservatory of Art and Craft in this event, and particularly Adrian Page. The collaboration between our institution has been engaged since 1999 in the area of international combustion engines and thermal machines. The result is this collaboration has been significantly developed and confirmed in the field of education, technological research and innovation, dissemination of scientific and technical culture. Participation as research associate of the University of Pitești in our laboratory is supported by our institution that are involved in this program by funding several partners. Two joint PhD were also supported, Katalin Zaria and Victor Yorka, which are here present. This work regularly leads to common publication and presentation at international conferences. Two video conferences organized at NAM on the theme of variable compression ratio and variable bulk actuation have been presented thanks to Adrian Clenchit and Adrian Vita. Common papers of this subject have been recently published in a well-known review in France, the review Technique de l'Ingénieur. I also want to thank French and Romanian Agency of Research and also Eureko and Erasmus for the support. The Office of French Research and Higher Education, IRS, recently has encouraged our laboratory to amplify the common synergy between our institutions. That's what we are going on. I also want to take advantage of this Congress to make some advertisement about Congress COFREC 14, which we organize next year in April. This is a Congress organized every 2 years in France and in Romania, except last year. This Congress was organized in Sotopol in Bulgaria. Here is an international committee. Language of the conference is French, but communication in English are welcome. A lot of topics in English, yes. Lots of topics are covered, but concerning mainly energy, chemistry, and thermodynamics. Our website is in construction, but I hope that major information will be available at the end of this month. Mail address is already functioning if you want to contact us. So, mulțumesc pentru atenție.
Thank you, Pierre, for your kind words. Let me welcome my colleagues and friends from Brașov and Schaeffler Brașov. And right now I would like you to invite you to take a place in front of the screen, as I would like to introduce the subject of our topic, of our meeting today. So thank you all. You all know the program of our meeting. As you say, we're going to soon begin with Giovanni Cipolla from Politecnico di Torino, former GM Powertrain. Next, Eduard Golobataille-Schmidt, Schaeffler Technologie, Germany. Stéphane Guillan, after the lunch break, which will be held here for everybody, from Renault France, Hubert Friedel from AVL Austria. Unfortunately, Romain Le Forestier, he broke his leg, so he's in France right now. So I will end the day with my presentation. You are maybe asking yourself, why organizing this workshop? It's simple. The Vice Rector Brăslaș told you there is a history, there is a tradition here in my university on this topic, on the topic of variable valve actuation. And let me briefly present you some dates. In 1977, a mechanical cam phasing device was applied on the gasoline engine of the four-wheel drive RO vehicle by Professor Dumitrescu and his team. He continued to work on this subject until, let's say, 1990. Between 1985 and 1990, Professor Krista, who is here with us, worked on this subject and created and tested several solutions. Last but not least, I would like to mention my professor, Professor Hara. Myself, I'm working with him since 1997. At that time, I was about to end my master's degree, and here are some pictures, some figures about our evolution. It's about my work with Professor Hara. I have to say that between 1985 and 1990, 2 engine prototypes were built with the aid of Dacia Plant. In my first period with Professor Hara, I was working on variable compression ratio, which is the subject of my PhD thesis. But in 2005, we decided to relaunch the subject of variable intake valve lift, and here is the first engine prototype featuring a carburetor and a manual actuation of intake valve load. We continued to work on this subject. We applied the single point injection. We added an automatic actuation of intake valve load, and in March 2006, we succeeded to prove the ability of throttleless operation of our engine. As you see, it's about a single point injection, and we obtained a stable idle operation with, let's say, a very lean mixture. Certainly, we wanted to bring our engine up to the present, so we mounted a multi-port fuel injection system on a cylinder head featuring intake and exhaust on the same side. We even tried to adapt our prototype engine on a Dacia Logan car in order to draw, let's say, frank and direct a bit more attention to our work. And we've arrived in the present. We wanted to have a more adapted combustion chamber to our engine, so we made an adaptation of a cross-flow engine head with a hemispheric combustion chamber, as you see here. This engine is currently working in my lab, and in a single slide, let's see the evolution. As you see here, it's not only about the variable intake valve lift that I will present later on. It's only about a combination with a variable compression ratio, and my professor, Professor Hara, and myself, we are calling it the adaptive thermal engine. So this is the explanations. I think they were necessary in order for you to understand why organizing this workshop. At this particular moment, I would like to really begin the presentations, and I propose you, because we started a bit later, I propose you not to make the break, but to begin with Giovanni Cipolla, a good friend of ours, and he will tell us about variable valve actuation. Why? A good topic to begin. Giovanni, please. Thank you.
unfortunately, I think we're going to need to have the break that I was trying to avoid, because the file of Giovanni is not converted to the current. Please excuse me, 5 minutes of a little break.
Going out again in detail. And so we are using the volumetric efficiency. At the end of the story, the fact that we have this variability of volumetric efficiency, and we have also variability in thermodynamic aspects, at the end of the story, we don't have the performance of the engine that are constant torque or linear power versus the engine speed, but there is a shape of the torque, and so a consequent shape of the power, that is not what we could expect from a theoretical point of view. And that's the operation of the internal combustion engine at what I call the full load. So it's a wide open throttle, when we press 100% the accelerator. But usually we don't use the engine always at maximum power. When we drive every day with our cars, we are not pressing the accelerator to the maximum. So we are operating not just along this curve, but we are operating in any location below this curve. And whatever. If you consider it to be at the fixed engine rates, and you are changing the load, like here, you see that the volumetric efficiency changes along the load, but even the combustion efficiency, the mechanical efficiency. If you multiply these three efficiencies, the total efficiency of the engine can be shaped like this. This is just indicative, it's not an absolute value. And the same happens if you change at fixed load the speed of the engine. You have the combustion, the volumetric efficiency, the shape will be this one. That's because of some resonances in the intake or the exhaust pipes. You have some combustion efficiency that go like this, and you have a mechanical efficiency like this. At the end of the story, you have, again, not a constant efficiency now. So what happens is that I have an engine that is very well known, the engine maps or onion maps. That means that we don't have the maximum efficiency of the engine in all operating range, that is all engine speed and all engine load, but just in some location that it is there. But when we are moving versus low load or high or low speed, we are deteriorating this efficiency. And because usually the engineers don't use efficiency, but we use the reciprocal. That is the fuel consumption, that is the gram per kilowatt hour. This is the same map, instead of being three-dimensional, bidimensional, and instead of having constant line of efficiency, there is a constant line of fuel consumption. But what we must keep in mind is that unfortunately an engine doesn't have a constant efficiency all over the engine map. And keeping in mind the fact that when we buy an engine, we buy an engine with a certain maximum torque, maximum power, but we are very seldom use a high performance condition our engine. We are using in our conventional driving cycle or urban driving cycle, but many times the homologation is done in another areas. So it means that in order to optimize what the customer wants, that is to have a maximum good performance engine, but good drivability, but also that is compatible for the homologation, means that you have to work a lot from the calibration or control system in order to optimize the performances, the fuel consumption, and the emissions in all the engine units. And that's a big issue for an engine. And that's the reason why it could be very useful to have some variable capabilities in the engine in order to make the life of the engineers easier and the end to have a better engine. So this is a very basic reason why variability.
So let's talk what are the variable components, the variable technology that have been developed, envisaged, or used in internal combustion engines now. Sorry, the title is hidden because we have modification in the file, sorry. But when you are talking about the variability or controllability in an engine, there are three different layers. The first layer, that is the kernel, is the compression ratio. Because when you start to design an engine, one of the first things you define is the bore-to-stroke ratio and the compression ratio. And that's the preliminary aspect that causes strong, important effects on the efficiency and emission of the engine. The second layer is related to the other controllable devices. Throttle, I'm talking about gasoline in this case. If you want to change the load, the torque of the engine, you have to change the amount of air and so the amount of fuel you put in the system. And so you need usually to throttle, and the throttle is a variable device. We will go and discuss it later. The other is fuel injection system, where you have to control the amount of fuel per cylinder, per cycle you inject, operating on the control unit that is based mainly sometimes in microseconds or milliseconds of excitation of the injector. You have another variable device opportunity that is the turbocharging. Could be different kind of charging turbocharging. The intake and exhaust manifold, the valve operation, and the exhaust system that is what is related to the EGR system or the DEWA system and so on. Let's go one after the other with variable devices. The variable compression ratio. Here is another diagram that has the same message that changing the compression ratio will change the efficiency. So the idea is that I use the maximum compression ratio because I increase the efficiency. Unfortunately, if you increase the compression ratio above a certain limit, you can have, in the gasoline case, some problem of combustion, that is the knock. In the diesel, you have the problem of maximum peak pressure that can deteriorate the engine reliability because it stresses too much the engine effect. And so, at the end of the story, for the not turbocharged gasoline engine, use a relatively high compression ratio. For the turbocharger, you have to reduce the compression ratio because of the knock problems. And you see here the trade-off between the fuel consumption and the performances of the engine. With the variable compression ratio, you can arrive to a situation in which you use at partial loads a very high compression ratio, because at partial loads you don't have a problem with knocking, and so you take advantages of that. But in the meantime, when you are at the maximum power, you can reduce the compression ratio along this line, and so at the end you have an engine with good fuel consumption and good performance. There have been developed different devices to do that. Here, for example, one is to move with some papers the distance between the cylinder head and the block. It is a bit complicated, but it has been done in some prototypes. The other is a solution that has been proposed by an engineering company, is to attach the location of the bearings and the main bearings and to change the position of the crankshaft versus the cylinder. So it's something that is feasible, but it's not so easy to do. I mentioned throttling. Throttling is the throttle body. The throttling is a device that is needed in order to reduce the amount of air and so fuel that is operating in the thermodynamic cycle. But in addition to this, throttling is also causing some negative thermodynamic cycle because you have to suck to make the intake at the low pressure and to discharge at higher pressure, so you have a negative thermodynamic cycle. So you are controlling the amount of mass operating in the cycle, that is your target, but unfortunately you have some pumping losses, so you have to spend some work with the other pistons in order to move the engine that is operating in this part of the cycle. So throttling is a need, but cause some deterioration in the engine efficiency. You can see here throttle body, that is what is usually utilized for controlling the amount of air. Here is the same, but it is integrated with throttle body in that unit. Another variability aspect that is needed and used is to have a variable intake manifold. The reason is that you have different volumetric efficiency depending on the length of the intake pipe versus speed. You can see here if you don't have intake, because the idea is the intake is slightly stupid, causes some pressure losses and so some deterioration. And in fact, when you operate in high speed, you don't have. If you look at the Formula 1 engines, they have an intake pipe around the length of 50, 60 or whatever millimeters. But when you are reducing the speed, you discover immediately that if you have some longer pipe, you can improve the volumetric efficiency because you have some inertia effect of the air column in the pipe, and because you have a positive aspect of the wave action in the pipe itself. So, at the end of the story, it would be useful to have not a fixed length pipe, but to have a variable one that could be realized like this one, that is a Volkswagen solution, that is like a scroll manifold in which you have 2 or 3 different levels of length. Or the other that is the Ferrari solution for the Enzo that is like a trumpet, so a variable length pipe. After that you can move to a turbocharger engine, and in the case of the compressor side, if you look at the compressor map, that is something like this, the black-gray lines are the constant speed, constant efficiency values of the compressor, and you put there the operating condition of an engine. You see that in maximum power, many times, the compressor is operating at too high speed. That is what is called the choke line. So it's something that is the maximum, even you are able to have more flow, even though you increase the compressor speed. The other is that when you are in the area of maximum torque, or you're using the wide EGR system, you are going what is called the choke line, and so you have some reverse flow from the high pressure to the low pressure compressor, and so keep deteriorating the efficiency. And by the way, moving in this move, because the maximum efficiency is there, means that here you have a low efficiency, here you have low efficiency. When you have a partial load, a low speed, you have the engine, the turbocharger that is unable to give you the boost you are looking for. So based on that, the idea is that to use a variable compressor in which instead of having a single map, you can shift the map versus the left or right side in order to match the engine and the turbocharger in the location of the better efficiency. The other is variable devices. So I'm moving the engine from the intake versus the exhaust. So after the compressor, I found the valves, and the valves can be variable. The variability could be a variability of the timing, so you shift the opening or closing of the intake and the exhaust versus crank angle. Could be a variable lift. You change the opening, the millimeters of opening of the valves. could be a combination of both, so we can obtain something like this, something like this. So the variability is of the valves can give you the flexibility to have a different discharge coefficient and effect, or to tune the opening and closing event when the right wave action happens in the intake of the exhaust mechanism. Last but not least, there could be also the system that is not operating with cams, that is called camless. Could be a device that has been developed by some researchers in Germany or in England. And the one is the German is the electromagnetic system, the English is the electrohydraulic system. And it's something that there is some different actuators, could be a coil with electrical magnetic or a piston with some pressurized oil that open the valves instead of the cap. After the engine, I have the exhaust. On the exhaust, I have the turbocharger. The turbocharger, the turbine, sorry. The turbine turbocharger could be with so-called wastegate. The wastegate is a valve that is in parallel of the turbine wheel, and the exhaust can pass through the wheel or directly to the exhaust by means of these valves. This purpose is in order to limit the power supplied by the turbine to the compressor and to control the boosting level. Here you can see some advantages. The advantage that the target is to have a certain power, that is a certain boosting level. With a big turbine, you can have this shape like this, but if you utilize a small turbine, you can obtain a curve like this one, the red one. But unfortunately, if you don't control the maximum pressure, you arrive at pressure that is unacceptable at the maximum power. And so you need to open the wastegate and to discharge some of the exhaust that you don't need later. Instead of a wastegate, you can have a variable turbine that is a more sophisticated system. In this case, you have some nozzle with blades, and changing the angle of these blades, you can change the opening, and so the areas of passage of the gases, but also the angles in which these gases enter in the window of the turbine. And in this way, you can optimize the efficiency of the turbine itself, because you can see here, depending on the location of the blades, there is a nozzle opening, and you can have different efficiency. On the exhaust side, another variable device is what is called the exhaust gas recirculation system. That is a purpose when you are operating a partial loads in gasoline and diesel engine, not to have the cylinder plated with air, but in the significant portion of exhaust gases. The reason is that if you have air, means you have oxygen, that is what is used for combustion, but you have also nitrogen. And at high temperature, it is below above 2000 Kelvin, you have a problem of formation of NOx. That is a pollutant. The idea of EGR is to put exhaust gases in partial loads inside the cylinder, where you don't need so much a big amount of air, and so there are less air, there are less nitrogen, and because of less nitrogen, you have less NOx formation in the air. And you can see here the trade-off, that means that you can no, sorry, this device, sorry, this diagram is another slide. This device can be obtained what is called the high pressure EGR or short loop EGR. That means that I collect the portion of the exhaust gas on the exhaust side, and I send it to the intake by means of a cooler, because I can't send the hot exhaust gases in the intake. Or could be what is called low pressure EGR or low loop EGR, instead of having the gas upstream of the turbine and downstream of the compressor, you can have the gas collected downstream of the turbine and the catalyst system and the after-treatment system and save upstream of the compressor. Or you can have the combination of both, and you can have more flexibility in the amount of exhaust gas circulation you can manage. Last but not least is the variability on the exhaust line. There is the variable exhaust distribution. When you are operating an engine, if you have 4 independent manifolds, or you put together them 4 in 1, you can see that the performance, that is the net efficient performance, are changing versus engine speed. So usually we are engines that are always with a 4-in-1 solution or 6-in-1 or whatever, because at the end we want to have just a single after-treatment system. But in this way we don't have in all engines speed the maximum of automatic efficiency, because there are some cases in which the independent are different one. And so we think a lot of different solutions. One is the Yamaha solution that is using some total device between the manifold and the exhaust system. The other is being used by the Ferrari on the 550, that is a switchable device inside the engine mount. So there are many technologies available. All of them are a little complicated, and that's the reason why very seldom you find all of them together. Never you find all of them together. Very seldom some of them together in man. But I mentioned before that one of these solutions is the DBA, and so I want to explain why the DBA seems to be one of the more attractive interesting solutions for the controllability of internal combustion. And I need to start with the basic concept that when you have a pipe and you create some disturbance in one side of the pipe, you create some sound wave that is moving longitudinally along the pipe. It means that there are along the pipe some areas in which there are high density and other low density of the gases. And this situation is not fixed, but it is moving at the sound speed along the pipe. And it could be also considered in a mechanical equivalent, that is in the spring, in the coil spring, because disturbance in one coil, and this disturbance is moving around back and forward around the coil. So what happens at the end, there is some wave action, that is the red one, so a wave of pressure, and because of the fact that there is difference of pressure upstream and downstream of a unit cell of air, that causes some movement of this mass in one direction or the other. And you can see on the blue one the movement of this mass. So at the end of the story, in the pipes, there is not a constant flow from the intake, from the filter versus the engine, but there is always some wave action that the air is moving up and down. That is something that is very familiar with the people that are interested in music, because this effect of the wave action in open-end or closed-end sites are very common in organs, in which if you go in the church, you can find pipes of different size and different length, and each of these have a different sound. Sound means frequency. Or you can use a trumpet. A trumpet is a device in which you have a long pipe like this, and by means of some valves you can open or close different channels, and so you utilize all the length or you bypass one portion of the length, and you obtain different sound, different frequencies. Last but not least is the trombone. Trombone is a continuous variable pipe in which you can elongate or make shorter the pipe. So that happens also in the intake and the exhaust manifolds of the engine. And that's the reason of the variable intake system, variable. And you can see here what happens during an operation. I have to start from the beginning just a moment. On this diagram. There is the valve that is the green one that is closed, and so there is the atmospheric pressure in the pipe. When the valve is open, the piston is causing some pressure reduction, and this pressure reduction travels along the pipe with the sound speed, and afterwards, when you close the valve, at a certain moment you have again the ambient pressure. So it's the piston that is generating this wave action, but unfortunately the piston is operating at its own frequency. When an engine is operating at 6,000 revs, and it is a 4-stroke engine, it means that it is making one cycle in fact it is making 6,000 divided by 2, so 3,000 cycles per minute means a frequency of 50 Hz. When it is running not at 600 but at 6,000 but at 3,000, the frequency of the excitation of the engine is not anymore 50 Hz but is 25 Hz. But unfortunately, the pipe have a response frequency that is fixed, if you have fixed geometry. And so at the end of the story, you can have a situation in which the pressure wave in the intake and exhaust are the blue and the pink line, and you have to open and close the valves accordingly when it is arriving at the right high pressure or low pressure in the intake and the exhaust. If you open the valves when you have the wrong pressure, instead of having a good volumetric efficiency, you are deteriorating the volumetric efficiency. What the engine designer is doing is defining the valve timing and the valve opening and closing in order to have this right tuning between the wave action in the intake and the opening and closing the valve, the right for what is the design point. Usually the design point is around the maximum torque of the engine. But when you move out of the design point, you see that the pressure wave action changes completely. You can see here different engine speeds that the amplitude, but also when versus the cantilever happen, this high pressure, low pressure in the manifolds is completely different. And so the only chance is to operate on the valve timing in order to optimize the opening and closing at different speed and also different loads in order to match these, to have a better fuel. And that is the reason why the main variable devices have been developed. The more promising one will be discussed today with the when you design an engine, I mentioned that usually you design to obtain the design point around the maximum torque, but depending if you're designing an engine for light trucks or for high performance vehicles, you can decide to have the maximum torque at low speed or high speed. That means that you use a large or a narrow valve overlap. And with the variable valve timing system, you can obtain instead of this curve or this other curve, the solid line that is at every engine speed you can set the right valve timing unit. The other advantage of variable valve devices is that you can operate, it was mentioned by Adrian in the presentation before over the throttlerless engine, that you can control the load of of the engine, so the performance of the engine, the partial loads, we reducing the negative aspect of the pumping cycle during the intake and exhaust by operating with some device in order to close the valves later, the intake valve. And so in this way you are reducing the charge because you are sucking without opening some air, but you are not utilizing in the thermodynamic cycle because you discharge the air. And the advantages in fuel economy are significant. As you can see here the values. At partial load, low speed, the variety is around. The other advantages of the variability of the valve system is that you can control the air motion inside the combustion chamber. Because if you have two intake valves, you can open in different way one or the two valves, and so you can create different motion that is called swirl if it is a rotation around the axis of the cylinder, or could be thunder if it is orthogonal vector. So this kind of rotation is thunder, this one is whirl. And by means of operating with the variable device valves, you can control the flow field and clean the mixing process between the fuel and the air at the end of the story, the combustion. And the other point is that you can control, you can also control the turbulence. That is the term, the parameter here is the kx, there is a parameter of the turbulence, there is a parameter that is enhancing the combustion, increasing the kx value of the turbulence value, you increase the combustion the velocity, so the efficiency. And you can see that with the throttle case, you don't have the right or uniform distribution of the turbulence inside the combustion chamber with the variable adaptation of the energy. The other point that I mentioned that we are interested to have a variable compression ratio, to have the maximum possible compression ratio, that means to have a variable compression ratio, and with the variable timing, you can change the position when you close, for example, the intake valve, and so you can have any compression ratio between the maximum geometrical one to the minimum. So it means that at partial loads you can utilize one compression ratio higher than the full load. Another aspect that is very useful is the ability to operate the timing of the valves is to have a different expansion stroke versus the compression stroke. In the conventional engine, you have a fixed, a single compression ratio in the compression stroke from V1 to V2 and expansion from V2 to V1. That means that you open the valves when there are pressure inside the cylinder, and so a significant amount of energy available you don't use. If you are able to have a longer stroke of the piston during the exhaust, you can recover some of the energy. And then the idea of the Miller-Atkinson cycle, that is that you have a longer expansion stroke up to there, and the compression stroke from here only, and so you are recuperating this energy. And this energy is significant. You can see here what it does it mean to have or not to have this recovery of this lost energy utilizing the Atkinson cycle on the rear engine. With the variable valve actuation, you can do that when you need it, because you can decide to close the valves and the intake valve later on, and so you have the compression, the real operation compression ratio that is starting from this point up to there, and the expansion compression ratio is going up to there. Another point I mentioned, EGR. EGR is obtained by means of external piping, but could be also obtained with some internal EGR. That means at partial loads, I don't clean completely the cylinder, I don't exhaust all the burn gases in the exhaust pipe, but I maintain some residual gases inside the combustion chamber. And that is called the internal EGR. That is useful in partial loads, and it could be with a variable device obtained. You can see here that you can open again the exhaust valves when you are in the phase of near the closing of the intake valve, or you can open the intake valve when you are opening the exhaust valve. In this way, you trap some residual gases inside the cylinder. And that can be done, and you can see here, because of the pressure difference between the exhaust and the intake during these events. And you can see here is a backflow of exhaust in the cylinder, and here is a backflow of exhaust in the cylinder in the two cases of reopening of the intake valve or opening, post-opening exhaust. With the variable valve actuation and mainly changing the intake valve closing, you can also modify, apart the performances, also the emission of the engine. Here, all the diagram I've plotted, for example, here the carbon monoxide and NOx versus at constant speed and constant loads, the different valve closing events. And so the flexibility in valve timing is a device that can reduce the engine out emissions with the advantage that you don't have to convert in the catalyst later on a big amount of pollutant. Last but not least, and that's more applicable mainly for the diesel engine, for the light truck engines, is that if you have a variable device, you can have a good braking, engine brake effect. Diesel engine doesn't have a good brake effect like the gasoline. With the gasoline, I close the throttle and I have a negative throttling cycle, and so during a slow down, I don't have to use so much the brakes. In the case of diesel, it doesn't happen because I don't have the throttle. And there are different devices. One very famous is the Jacobs device. But with the variable valve timing, you can also, do like this. You can open the exhaust valves during the compression stroke of the engine. That means that the piston compress, there is an intake phase, after that there is the compression of the cylinder by the air by the piston, but you discharge this air in the exhaust, and so at the end you have another negative cycle that causes some braking effect of the engine that is useful in some operating conditions. And you can see here the difference without and with this device of reopening the exhaust valve during the slow down of the vehicle from the braking effect. And believe me, when you are in the Alps or in the mountains of Italy or with the very big lorry, it's very important to have a very valid braking effect in the So the conclusion or the final remarks from my 1 hour speech is that the internal combustion engine needs variable devices, because the internal combustion engine mainly in automotive, I'm not talking about electrical generator, and different operating conditions, wide operational field, transit operation. It's important to have fuel economy in real use, but the limiting driving cycle. And there are other aspects to be considered. And the variable capability is one, and we went line by line in the whole video. What I hope that I explained at the end, in the last part of my presentation, is that the variable valve actuation can do many of these tasks with a device that is probably more simple, more reliable, and more economic than all other devices like compression, the variable compression ratio, or variable intake and exhaust. Okay, so I conclude this presentation. I thank you very much much for your attention, and if you have any questions, I'm available.
Just a small question, Giovanni, if there is nobody else. I've seen you spoke about EGR, slide number 20, and I was asking myself, and it's maybe a question not only for you, but for our other colleagues as well. If we have double cam phasing devices on intake and on exhaust, is it an interest of using EGR at gasoline engines? This is my question. Is there a gasoline engine that has in the same time an EGR system but a VVT system? No.
You might mention there are other experts that can give you the answer. My answer is the following. First, in the case of the gasoline, the EGR amount is not so, there is not a requirement to have so large EGR as in the diesel. So it's not so critical to have an EGR without, the variability on the exhaust side, variable rotation on the exhaust side of the gasoline could be considered for different reasons, and not just for the reason of diesel. But the diesel is the difference. I don't know if you have some comments.
I think we're on the back presentation to this slide.
Thank you. Thank you.
Okay. Any other questions? Curiosity?
So today also everyone, so I'm very happy that you explained all the details so precisely that gives less work to me in my afternoon presentation, because I can build upon these basics you all have received up. One comment from my side. So I'm from gasoline engines, and from school I have learned, as you have shown in your diagram, when increasing the compression ratio. The higher the compression ratio, the higher is the efficiency. I personally always wondering, so gasoline doing this exercise, so increasing the compression ratio. So there's one engine on the market already having a compression ratio of 14, and I do not understand diesel that way. I'm surprised that the diesels go down, and I expecting maybe in a few years the compression ratio of the diesel, which used to be 20, meet the compression ratio, has the same compression ratio like a gasoline engine.
The gasoline reached the value of 14, and thanks also to the better understanding of the combustion process, to avoid knocking, to the better fuels, and so on. The higher K epsilon, and so the higher velocity of the combustion. In the case of the diesel, when we started, there was not only short, but with the diesel, the compression ratio was 22, something like that. But it was not a direct injection, but it was a per-channel injection. So you need a high pressure, because in the diesel, you need to have at the end of the compression stroke a chamber such to have it out of the And because of the pressure losses in the per-chamber throttle, connecting the per-chamber and the combustion, you have some pressure decay, so if you don't have this high value of compression ratio, you have a problem of the ignition of the fuel. The other point was that you need to be able to start the engine when you start in Sweden at -30°C in the winter time, and so you have a problem that if you don't have high compression ratio, you are good. Now with the direct injection system, with the glow plug, with a more controllable injection system thanks to common rail, probably 22, 20 not much, and the effect is moved to 18, 17. The reason that is reducing further is that there is a diesel limit of the maximum pressure because of stresses of the engine itself. And stresses can be overcome making more robust truck. A more robust truck can be used to have heavy engine or more stress. And so the idea is that I maintain the compression ratio high enough to have ignition, but allowing me to have a high boost level because of the trick of the diesel to reach a very important specific maximum power and to have high compression. So there is I agree that, but luckily, and that is Carnot, there is an assist. So moving from 20 to 16 is not a deterioration so much.
Maybe gasoline diesel somewhere in the middle.
Right.
Yes, one question. Maybe one additional question. What is your vision about the introduction of variable valve lift and variable valve time in diesel? Because of gasoline, okay, it's already in production. Do you see a real interest on diesel?
Yeah. You quote a very interesting question that is in discussion among the engine engineers in this period of time. Yes, diesel advantages, first of all, is the controllability of the air motion inside the combustion chamber. Because the combustion in the diesel is very dependent of the mixing process between the droplets of fuel injected and the air. You have to optimize this process, and by means of controlling the lift of the valves or opening, for example, if you have two intake valves, the partial load you need just one is more than enough. And this way you can have a strong swirl effect, and in this way you will increase the air motion and the air mixing in the fuel. The fuel is in the air. The other, and you can do everything in between, because you can open one more, the other less. The other is that you need to increase a huge amount of EGR to reduce the NOx. And if you can rely on more amount of residual gases, it is internal EGR in the combustion chamber is useful. And the other point is that because the diesel engine has a good turbine, you can, with the variability in the exhaust cans, you can control the enthalpy, so the energy of the exhaust in the turbine, and so widen the operation condition and the transit, mainly the turbocharger. Last but not least, because the soot formation in the combustion chamber is generated during the beginning of the combustion. So if you open the exhaust valve immediately after the ignition of the fuel, you produce a lot of pollution of soot. Luckily, the soot that is carbon burn during the expansion stroke, and what goes in the exhaust is just a receiver again. If you are able to control when you open the exhaust valves, you can reduce the amount of soot. But you need maximum power anyhow to open the valves earlier. So that means that with the variable device in the exhaust system, you can partial loss control the soot, maintaining the performance of maximum.
But with the difficulty of the higher compression ratio.
The problem of the difficulties are as follows. First, is dealing with the variable device on the outside is the more difficult than the closer. The second is unfortunately the diesel is more expensive and the variable device will increase the cost. And so you add in some other expensive device. Okay, thank you again.
Thank you, Giovanni. I would like to invite Edward Golovatai-Schmidt from Sheffield, Germany, and know that once he finished, we can take the lunch and we can enjoy easily conversation, a cup of coffee or so.
Ladies and gentlemen, I'm in the lucky position to speak today in front of you, not at least because I understand your language, and I would like to tell you some words about me. Eu m-am născut în România, am studiat la Timișoara, am terminat facultatea cam cu 10 ani înainte de cei mai mulți dintre voi studenți s-au născut. Și de 25 de ani mă ocup de actuația variabilă a subapelor. Now, switch again to English. I would like to tell you today some words about the consistent enhancement of variable valve actuation at Sheffield. As you know, our company is a very huge company, and we work the first in the world to introduce variable valve actuation in mass production for large volumes. I would like to speak today about this topic, the motivation to use the valve actuation, process of conventional combustion engine, overview of different variable valve rates, degree of improvement using this, and the variable valve training combination with sequential turbocharging of the engine. At the end, I will come to some concluding remarks. Oh, yes. Probably I should do it something like that. You probably have, all of you have heard that the most of the legislation in the world are focused on reducing fuel consumption, and if you look what happens in the world, in the United States, Australia, China, Europe, South Korea, Japan, you can see a continuously decrease of fuel consumption at the engines. And if you are today at about, in Europe, let's say, at about 140 grams per kilowatt hour, we will come to 95 in 2020. This means a huge amount of development work which should be done regarding the engine, the transmission, and the whole vehicle. But this means additional that we will need to find another degree of variability in the vehicle in order to optimize them for every running behavior of the vehicle. If we look at it, go a little bit faster. If we would consider to have crude oil, which is, let's say, which contains 100% of the energy, at the petrol station, we will find 7% less of that because of the refinery process and the transport to the petrol station. From the petrol station to the engine, the energy loss is another 2%. Then we come into the engine itself, and we will lose some 5 to 8% based on the energy loss due to the charging process. Heat losses in the coolant are about 25%, in the exhaust pipe another 25%, then we have mechanical friction in the engine, which gives us, let's say, 8% or 9%. Auxiliary drives with 2.5%, powertrain losses with 3%, and in the vehicle we will have some braking losses of 4%. So at the end, from 100% energy contained into the crude oil, we will get about 14–50%, and other studies relate about 10%, which comes on the wheels in the vehicle. So, if we look at the engine itself, the variable belt actuation could influence this from here to here, all these processes. And Professor Cipolla has shown us the basics, how the influences of different types of variable actuations act on these characteristics. The process in a conventional engine is the next point I would like to approach. And the technologies which are necessary in a gasoline engine in order to improve its quality is to have a variable charge motion, to have a variable valve actuation in order to open and close each valve at the optimum time depending on the driving behavior. Then we have stratified GDI, which is gasoline direct injection, the stratified one. We have controlled auto ignition, which is the technology of the future. Nobody knows if it will once come in serious production, but everybody works on it. We have cylinder deactivation, and we have turbocharging or supercharging. These parameters are influences the engine efficiency. Cylinder deactivation and supercharging influences the operation point of the engine. What is important to have an engine to reduce catalytic losses, to improve energy management, and this can be done by improved thermal efficiency and improved friction and energy management. Our products, which are related to variable valve actuation, are in fact all tailored specifically to do this and this. So, if we look at how we can improve that, something is wrong with my microphone. If we look how we could improve the fuel economy or the energy savings in an engine, in the operation point, we can look at a natural aspirated engine, which looks like something like here, and the best fuel economy is achieved here in the green area, and this is the energy necessary to drive the vehicle at 90 kilometers an hour or 120 kilometers an hour. So we can see here that we are not in the optimum point. So we lose some energy, which can be by optimizing the efficiency of the engine can be improved. If we have a turbocharged engine, we can see with this vehicle characteristic, we can see that we are worse than it was the natural aspirated engine. So okay, but I can do this. I can do this. Thank you. So we can see with a turbocharged engine we are worse than we were with a natural aspirated engine. But what is necessary now is to adapt the transmission and the vehicle to the new engine. If we design the transmission in order to have this vehicle characteristic, we can achieve exactly the best fuel economy by using a supercharged engine. So, if we look at characteristic, the mapping of an engine, we can see that the wheel consumption is very good in this area and is absolutely worse in this area. Giovanni has shown us that the homologation of the vehicles are made in this area, and the main working points of the vehicle are something like there, where the consumption is not absolutely good. So what we can do in this case is we can see here we have the losses based on gas exchange. These are the losses based on energy heat with the engine, which goes in the coolant, and this is the energy loss of the energy which goes into the exhaust pipe. But under throttle conditions, we have this loss significant because full load, we have them better. What we need to do is to design the valve actuation in a way that at part load, where generally the standard engine throttle, to design the valve actuation in a way that the throttle conditions to work, the engine should work like a G-throttle engine. This is exactly what Giovanni has shown to you also, that changing the opening and closing point of the intake and the exhaust valve, you can achieve the possibility to work at part load with the unthrottled engine. And as so far I understood, you have here in Pitești, Adrian has shown us an engine which works without any throttle, and that means a fuel consumption of probably 10 to 12% in a part load. So, if we would look at the mapping of an engine, we can see the intake valve, the optimum lift and opening and closing point of the intake valves, which is in this case idle, probably the valve should open there, very low and very short. In this area, it's probably important that the valve opens twice in order to improve the internal gas movement. At part load, we need an early intake closing, and at full load and high speed, we need a full valve characteristic. Giovanni has mentioned the Miller cycle too. And I would like to show you how the Miller cycle works in fact. Miller cycle doesn't mean anything else than opening, the closing, the intake valves before the bottom dead sector. That means in a conventional engine, if you work with a part load with throttle intake, you have a characteristic like this. And this is the negative load for the loss energy based on the charging process. If you open the intake valve very, very early before the top dead center, and you work with a full open throttle, you have just this amount of energy loss because closing the intake valve, you then you get the energy back, and you go further to the compression. The Atkinson cycle, which has been mentioned too, is a cycle where you open the intake and you close the intake valve very, very late. That means you, the diaphragm is like this, you go this way, and then you push out a definite amount of air which was loaded into the cylinder, and then you go into the compression. So you can reduce again the amount of energy losses from this amount to this small one. Another possibility we have with the variable valve actuation is to have port deactivation. The port deactivation means that one of the intake valves works at fully characteristic and the other one is closed. So in a diesel engine especially, you have a charging port and a swirl port. If you close the charging port at path low or the engine start, you will get a better swirl into the cylinder, which means a better mixture and a better burning process. So if you have the conventional engine with both valves open, and you have one just with a swirl port open, you get the heat release into the engine very, very optimized, and then you get a stable burning process. So, the valve phasing, which was mentioned also, the valve phasing is here in order to increase the overlap of the engine. And if we combine the valve phasing with the charging port deactivation, we get in fact a better mixture of the air fuel of the mixture, and then we come to a stable combustion. Here is shown in fact how these two systems work together. If we have the charge port and the swirl port, we can see reducing the valve lift of the charge port, we increase the swirl number, which is in fact a mass for the movement inside the cylinder. And we can see that this one, the swirl number increases by reducing the valve lift of the charge port, but at the same time, reducing the valve lift of the charge port reduces in fact the amount of air which enters into the cylinder. This is in fact exactly what we would like to have as part load, to have less amount of air into the cylinder and a better charge movement. Cylinder deactivation is also possible to have with variable valve actuation. This chart is similar to that what we have seen with natural aspirated and turbocharged engine. If we have an engine, let's say 8-cylinder engine, has a torque characteristic about like this, and has a best consumption point somewhere like here. If the half of the engine, let's say a 4-cylinder engine, would have this characteristic with the fuel consumption best point here, and the drag curve of the vehicle, it's the same, so we have the same vehicle. We can see that the 8-cylinder engine somewhere at the lowest vehicle speed, we will get a very low fuel consumption, reducing the amount of cylinders which works, we shift effect operation point, and if you reduce the 8-cylinder to a 4-cylinder engine, we can get the operation point of the engine in a point where the specific fuel consumption is optimal. What we can do with the variable valve actuation is, and this is a little bit more difficult, but you probably will learn it in your school. What we can do is at different operation behaviors of the engine to change the opening profile of the exhaust valve, which is shown here. We open the exhaust valve very late. In that case, we can create a situation like this to have a movement of the maximum pressure in the exhaust pipe, in order to make sure that even having a turbocharger, we can have a exhaust pressure, higher intake pressure, in order to keep exhaust gases into the cylinder. And that means a different behaviors of the engine. We would need different opening points of the exhaust valve in order to create the pressure peaks in the exhaust pipe to have enough exhaust gases into the cylinder at different operation points. So, if we look at the variable valve rates generally, we can say that we have two types of them, big types of them. The one is the phasing, which moves in fact the valve opening characteristic to early or to retard, and this can be done with the intake side or the exhaust side. But nowadays there are more sophisticated devices which can modify even the lift of the valve opening characteristic and the timing of that too. This one can be discrete, which are switchable for 2 or 3 steps, and it can be continuously. The 2 steps are here: captive, spider element, finger follower, shifting, cam roll lifter. As I learned, is that the Romanian language do not have a specific name for all of this. Is that correct? Yes, you need to invent some words for that, because in German and English we have specific words for it. Do you have them in Italian? Yes? Okay.
We can give you the native version to learn.
Oh, that would be a good idea. That would be a good idea. Because the Romanian language. Okay. So the switchable could be 2 steps or 3 steps, and the continuously, as Giovanni has mentioned, are electromagnetic, some mechanical or electrohydraulic. For the electrohydraulic, we would like to mention the Uniair. If we go to see the capabilities of different types of variable rates, which are typical for our company, for the Tesla company, which is the switchable technique, the switchable pivot element, which is the goal being follower, and shifting cam low. We can see that all of them have advantages and disadvantages, and have different capabilities to realize one of the functions I described before. Like this. So, the switchable technique is a 2-step switching element, and could not realize something with internal EGR crossing of valve events for 3 steps. The more sophisticated of our switchable variable block, right? Today is the switchable cameo. You can find it at the moment in some Audi engines and in one of the VW, the Volkswagen engines. They were developed in our company and we delivered the main components for it. And this one can be found at Porsche, Subaru, Volvo, and Jaguar. Switchable pivot element is installed in that Mazda engine, which was mentioned here with a compression ratio of 14. And the switchable pivot element, sorry, the switchable pivot element, I will not here. No, it's not. It should be this. Yes. The switchable figure follower can be found in some American vehicles or engines, especially from Ford and here. If you look at an overview of the systems which were invented over the years, this variable valve train, the first patent on it was applied in 1905 by Renault. And it was a cylinder deactivation, in fact, or a valve deactivation at that time. And there are some 1,500 ideas how to realize valve actuation systems, but from all that plenty of ideas, there are only a few of them which have been introduced in mass production. This is the fully variable valve actuation, and the BMW has a mechanical one, the Toyota has a mechanical one, the Nissan one, and this is it. We have a mechanical one which is eco valve, but it's not in series production by now. And there is a fully variable there is a fully variable hydraulic actuation, which is a fully variable valve actuation, which is installed into into more of Fiat models, which is called Uniair. And you from the University of Pitești have got a module yesterday of this variable valve actuation. You can see it in Professor David's laboratory. So, what is necessary to be done? What is necessary to be done in combination with variable valve actuation is first to model the engine. That can be done with a program called Power, so you can define the engine mark, the fuel consumption, and also the exhaust emissions. And then coming from the other side, you need to model the vehicle characteristic or the vehicle behavior, and then to put together the vehicle behavior with the engine characteristic to get the best performance of the engine, let's say in the New European driving cycle. The New European driving cycle is familiar for everybody, I respect. Okay, so this is the way how to model in fact the engine, especially we concentrate on the variable valve actuation. And then, if we look what we can model, the most important working points of the engine in the NADC is something like this. We have these possibilities to modify the valve actuation, and if we look how to optimize it, we find the intake, at least the intake valve, having this characteristic that you can see there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 with no valve. So the reliability cannot be defined in a simple linear way to say I can have one system of variability in order to cover all the needs of the engine. What we need to do here is to have something probably more mechanism incorporated into the same engine in order to realize this characteristics themselves. Additional to this, we will have, as I have shown together, we have some possibilities or some necessities to modify the exhaust valve opening characteristics. So you can see this is a very complex system, which is important to be studied very appropriately. Going now, this is an example of optimization which comes to stress what I said before. If we go with engine with low engine speeds, we would like an opening of the intake valve of 3.5 millimeters. Here we can gain some 9%, 9.6% using the valve lift of 4.4 to 4.7. In this area we can gain, we can save some fuel using a valve opening of 6 or 7 millimeters. Generally, the valve characteristic, the intake valve characteristic is between 8 and 11, or let's say 12 millimeters. So what we need to do is to reduce the valve opening and also the valve timing. So this shows the possibility. I would not like to enter into details with this, but this shows the improvements we can have using different type of variable valve actuation. This is the possibilities of Unier, which influences, in fact, in this direction, the parameters of the engine, and this is a phase shifter which influences in this direction. If we look at the intake pressure, the inlet pressure, and the throttle conditions, we can see that this one can influence less than this one can influence, because with this one opening, closing the intake earlier and having a smaller valve lift, we can influence, in fact, very good the inlet pressure of the engine. The same happens with the exhaust gas. In this case, this one, the phaser influences in this direction, where with the phases, with the valve overlap, we can influence very, very well the amount of exhaust gas remaining in the cylinder with the, with the Unier system, we cannot influence it at all because the overlap at Unier remains the same. This is shown in this diagram. Another parameter which is important for the engine, at least for the gasoline engine, is the combustion duration. In this case, this one influences in this direction, and we can influence very well the combustion duration at different operating points of the engine. With the simple shift up, we cannot do too much in that case. So, this is another type of optimization where the intake pressure is shown. This is very similar to what we had before. And now we should look at the degree of improvement of conventional engine. What we have here is that we have different possibilities to influence the valve actuation, which is a two-step full cylinders on intake side, a three-step full cylinders for cylinder deactivation. We have three steps where two steps are used for running the engine, and the other one is to deactivate the valve. And then if we have a basis engine, without any variable valve actuation, with a two-step we can gain 5.7%, with a three-step 6%, with a two-step with cylinder deactivation we get 10.2%, with three-step with cylinder selective deactivation we get 11%. What happens here is, this all is related to NEDC. If we see here that between 5.7 and 6% there is no big difference, but the complexity between a two-step and a three-step valve actuation is very, very large. So it would indicate us not to use the three-step. The same comes with the cylinder deactivation. Between 10.2 and 11 there is no big difference. So, but this is only a part of the story. The another part comes here, that NEDC is the new European driving cycle where the homologation of the old engines are made. But the real driving cycle in the real world is quite different. This is what Giovanni has shown us too. And there is a more dynamic driving cycle which is called Heisman. This one. You can see it's more dynamic, but it's a combination between inter-urban, extra-urban, and autobahn or highway traffic. And the main operating point of the engine, using the same engine and the same vehicle, you can see they are here, totally different here. And in the Heisman, you can see the following in the Heisman cycle, and this is the NEDC cycle with 11.2 and 10.2 and 11 savings. And in the Heisman, you have with the two-step cylinder deactivation, you have 3.3, and with the three-step, you have 7.4%. That means that in fact, this one, for the real world, which is for the real world, is more important than this one. And so the decision which type of cylinder deactivation we should use, or cylinder or valve actuation, variable valve actuation to use, it's very difficult to be done, but it should be calculated before simulated and then validated into the real world. So at the beginning, I've shown that we have the possibility with the valve actuation to improve the thermodynamics of the engine or the friction of the engine. And you can see here what possibilities are given to reduce fuel. With thermodynamic improvement, we can improve something with diesel, more with gasoline, but we can the gasoline engine reduce the pumping losses, which is probably the main energy consumer of the engine, the part load. We can also with variable actuation to improve the friction losses. We can imagine additional to valve actuation to have accessories controlled only by demand. That means that we have, for example, the alternator. The alternator works the whole time, even if the battery is fully charged. So in that case, it would be interesting probably to switch off the alternator. Or there are another consumers like the power steering, the hydraulic power steering. The oil pump runs the whole time, but you need that oil pressure just if you go around the corner. So for the improvements at the engine, for the improvement of the engines, additional to valve actuation are thermal management, downsizing and start-stop functions. The start-stop function requires also some variable valve actuation in order to have a smooth restart of the engine using the decompression. So we come now to the variable valve training combination with sequential turbocharging. The conventional turbocharging, the two-step turbocharger, means in fact to have a smaller turbocharger, a larger turbocharger. The small is called the high pressure, the other one is the low pressure. And we have a lot of gates leading the exhaust gases and the intake gases exactly how they should go in order to fill the engine properly at different working behaviors. What we can do with variable valve actuation, we have split ports. This means the exhaust port of one engine, the exhaust port of one engine, let's say this is the group 1, it's called group 1. Exhaust group 1, the other valve, it's called exhaust group 2. So we separate the exhaust pipes and put together all the groups 1, put together all the groups 2, and then by valve activation of group 1 or group 2, we can drive the turbocharger 1 or the turbocharger 2. And that is a solution which in fact thermodynamically it's more or less known from here what happens. But the turbocharger, the sequential turbocharger are absolutely expensive. They are, if one turbocharger costs, let's say, €1, the other one costs €1 too. If you put them together, you pay some €4 to €5. And with cylinder deactivation, which is cheap compared to this €5, you can realize a sequential turbocharging of the engine. And this is a technology which will be found probably from the next year in American German. Okay. We have the, as I explained, we have the three possibilities to activate the exhaust port group 1, the exhaust port group 2, or both. And in that case, both turbochargers work. And with that, if we look at the engine characteristic, we know that at lower speed, lower torque, we activate the one turbocharger, at higher speed, the other turbocharger. And we have also the possibility to activate the group 1, group 2, or both of them. So, in combination with the activation of the turbocharger, this is what I've mentioned when we had the exhaust valve, a smaller short lift of the exhaust valve, where you have seen that the pressure peak has moved compared to the standard valve opening. But in that case, we can, at part load, we can use this opening of the exhaust. The full load, we can use this, and in that case, we can activate the turbocharger, giving that more enthalpy to increase the speed of the turbocharger and the pressure load. So at very high load, can load both loops and then both turbochargers. This is what I mentioned before. And then what we can do with the sequential turbocharger is if we have just one turbocharger, bigger one, we can reach the full torque of the engine at definite speed using the conventional sequential turbocharger. We can reach that full load at lower speed. And with split ports, we can use it even, at lower speeds, probably directly from idle speed. I will come to the conclusions. And I put them here. Right. You have seen regarding valve actuation, there are so many possibilities, and nobody knows exactly how the over-next generation of engines will look like. But we as scientific people or production people, like my company, we need to be prepared for all the possibilities which will come in the future. And this is why we spend a huge amount of research effort using researching all the possibilities. What we know is that valve actuation has a... I've done something wrong. Okay. What's this one? What we know is that the valve actuation has a huge potential in reducing CO2. And the valve actuation is a key element for complementary introducing another technology. We have heard all of you about downsizing, about turbocharging, and valve actuation is a key element to enhance their functions. This is what we have done. And the drive cycle, as we have shown that idle and NBC, the driving cycle of the engine is a key element to decide which valve actuation should come. This is... I thank you for your attention, and if you have any questions, please ask me.
Remark. You were talking about synergies between VBA and some other technologies.
Yes.
And I think that slide number 33, you mentioned stop and start.
Yes.
Here in my university, we performed some tests with our variable lift prototype, and we reached an idle speed so low that we asked ourselves that it's
possible to do. Yes.
That it's perhaps better, once having such a system, not to apply a stop and start system, but a so-called sleep and start system. Why putting the engine to a stop rather than put it to a sleep? At a very, very low speed.
Yes.
We reached 470 RPM.
Yes.
Stable operation.
That is a great idea, which is the idea we had to. And but the start-stop or the stop-start is a behavior of the engine which can last 1 minute or more. And if you have a idle speed of, let's say, 400 or 500 RPM, the oil pump doesn't work anymore. So you would need something either to increase the oil pump, then you have an additional consumption during the other operation point of the engine, or what is possible too, and we work on it, to have an electrical oil pump to activate it during this period of time. So German, there is a speech which says, and now you can choose which death you would like to die.
Actually, we still had some oil pressure, but we didn't have water flow. So the engine easily...
Okay, the coolant doesn't
Yes.
work. This is, there are so many implications. This is what I mentioned too. There are so many different technologies which influences each other that if you have a good idea and a good advantage with one technology, you get some disadvantages with another technology, which makes it again probably not feasible. But this is why we work on it, on every of these technologies.
Thank you.
Maybe one question. You mentioned several options for having a valve actuation. I mean, it's really interesting. What is for you the difference in terms of precision and speed and response time between mechanical solution, I mean, apart from, and what is applied with the solution?
They are not comparable together, because if you look at the valvetronic, you can change the behavior of all the valves in one engine, in one cylinder tank. So then you have an additional disadvantage with valvetronic based on manufacturing tolerances of each mechanism. You get at least a lower valve lift. You get a difference of 2 or 3 or 4 tenths of millimeters. That some tenths of millimeter at full opening of the valve lid, which is, let's say, 10 millimeters, do not influence too much the difference between one cylinder and the other one. But if you go down to 1 millimeter, 3 tenths of millimeter after 30%, so the cylinders do not work similar. The one has more air, the other one has less air. The one has the fuel coming into the engine is based on the average of the cylinders. The fuel injection believes that all the cylinders are identical, and they are not. So this is the possibility we have with the mechanical actuation. This response of the mechanical actuation is high enough. It's high enough, but the disadvantage is that the part load, the cylinders do not work properly. If you have the hydraulic actuation, you can control each cylinder individually because every of the cylinder has a hydraulic valve. And then you need just a possibility to judge the functioning behavior of each engine. And that you can measure, measuring the torsional vibrations of the engine. You measure the torsional vibrations and you get some hints how every cylinder works. And then you can correct by using more or less fuel. You can correct or you can correct by opening more or less each individual cylinder. And then you have the possibility to make all the cylinders to work equally.
An additional question was, BMW example is that they can change the position between two engine events. And for sure, I agree it's adding some process difficulties.
I could tell you a story. BMW with the valvetronic is not a good example. Because there's another speech. If you introduce a new technologies, and within 5 years nobody copies you, the technology was not good. Okay. This is the technology of BMW was at the beginning very promising, but it doesn't work. Initially, they wanted to work throttleless, but it doesn't work because they open you now until 1.2 millimeters, something like that. And then the difference between the cylinder is too significant in order to continue to reduce the lift. Okay? Are there any questions?
Thank you, Edward. Let's have a lunch break, which is behind us. So keep
Okay, so I'm speaking now. I'm the design department of powertrain in Renault. I'm working in the south of Paris, in Grenoble. And so I'm what's called the technical expert in powertrain aerodynamics in the engine feeling. That means that I'm working basically on all the gasation process inside an engine that can be from thermomechanical engine, but also electrical engine, because we are cooling also, we have to cool also electrical engine and the battery. So that's my illustration. So today I would like to emphasize the synergies between new technologies, and we have spoken a little bit about that this morning, and you have shown already the pressure traces, but I will go more deeper in the details about that. About VVA systems and turbochargers, and applied on gasoline. Okay, so the plan of my presentation will be an introduction in order to explain to you what I was looking for. So I will have 3 parts. The first one where I will try to give you some information about the interaction between UPIT and turbos. So the first part will be what happens on the turbocharger when we try to reduce the pumping losses, and what we have to take into account when we have a low-time engine. The second one will be what solution to overcome the problem I described before is to improve the spare engine. So I will go perhaps a little bit more into details what we can do with a VVA and basically a VVT, but on the 4-cylinder engine, and after that the last part will be with a 3-cylinder engine, because you will see that the consequence of a number of cylinders should demonstrate a different synergies possible between VVT and tube. And then I will do the conclusion. And basically I will speak more about VVT than VVA, but during the conclusion I will try to give you what will be my recommendation in terms of systems with a full VVA system for overcome the problem of what I will see with the first part. Okay, so let's begin with the introduction. So it has been already presented. We have CO2 reduction we have to do. We have done on what we have to do in the future. So all the lines are different car manufacturers. Of course, I can show you only the line from Renault. So we have a target for 2015 of 130 grams per kilometer to meet. So we are all pacing to reach this target in the coming years. And we have a target of 95 grams per kilometer to meet in 2020. And what we do, obviously, is to improve the powertrain efficiency. So that will be the main topics of my speech. But what is already under study is the electrification of powertrain. We have spoken about stop and start, but there will be other devices also in order to help to decrease the fuel consumption, and the electrification will one solution. So basically it's a hybrid, mild hybrid, around that. And we have also, and it will be a big change for our credits from the vehicle side, we have to decrease the weight of all our vehicles, and we have also to work on aerodynamics. And here you can see that there is 2 lines. The first one is, and the difference just show the contribution of full IV vehicles. So it will be a bonus for us. It won't be the main trend. The main trend will be done by classical powertrain. In the meantime, we have to face some newspaper campaigns that emphasize one difficulty is that every car manufacturers have met their CO2 levels with a bad compromise with the real life fuel consumption, FPs for fuel efficiency. And so it will be in the future in West Europe we will have a WLTP cycle to meet. So we'll change the cycles. All the previous figures have been done on NEDC cycles. So in the future, we will move to a new cycle, perhaps more dynamic. That will be more dynamic for sure. That will be higher loads. And it will, of course, help us to increase, to work on real fuel consumption. Because nowadays, the vehicles are very optimistic in the advertisement in terms of CO2. It's not what we have on the engine. But as we have to meet the requirements in terms of CAFE, we have to go in that direction, but it's not fair for people. So, now if I have a look on the ESFC map of a gasoline engine, I can figure out different areas where I have to work in order to be able to decrease the overall fuel consumption. So basically, we have spoken about that. There is the region 1 that is related to the maximum fuel efficiency. So we'll see that later. Basically, it's the combustion ratio that is behind the optimization region. On the bottom, we have pumping losses, so I will come back on that later. There is one way to improve the fuel consumption, that is this region with low and torque. The higher is the low and torque, the lower will be the fuel consumption of a vehicle. We have also a benefit to have a higher torque level, and we have to take care about this region, that is the region of enrichment. That means that due to the constraints we have on the exhaust side of the material of the exhaust parts, basically what we do is to give more fuel than necessary, and then we have penalties when we go in a highways over the limits that are permitted in for instance in France. But not in Germany. So, if I come back to the areas, I would like to give you why we need to improve these areas and what we can do on valve and turbochargers. So basically, the area 1 is the intrinsic HP efficiency, so that means we have to work on the compression ratio. And so what we can do with the variable valve is to work on effective compression ratio, as explained before. And we have also to adapt the exhaust valve opening, because it is quite well known that for lower engine speed we need the best is to use the full expansion ratio, but at high speed perhaps we have to advance a little bit the exhaust valve opening in order not to increase so much the pumping losses. Of course, for this interesting HP efficiency, the turbocharger has no effect. Concerning the throttling reduction, the defrottling, so that will have an impact on the raw pressure indicated fuel consumption. What we can do is to have a late or early intake valve closing, that is in Maillard cycle or Atkinson cycle. And we can have adapt the exhaust valve opening for promoting internal residual gases. What we can do on the turbocharger, and I will explain this later, we can do some downsizing, of course. That's the main strength to decrease the fuel consumption of our gasoline engine nowadays, because that's already done for diesel engine. And so the replacement of large engine, natural aspirated engine by smaller ones. And what we can do also is to decrease the pressure before turbine under partial load. because nowadays, basically, we are all using the turbocharger, even the turbocharger is running and turning quite fast, even if you do not need the boost pressure. So it can be, it's a solution to reduce the pumping loss. So high speed, what I can do is to limit the emission to cool the exhaust. So basically what you can do is to have late intake pipe closing. That's one way to reduce the temperature and to have early exhaust pipe opening. And another solution could be to have a large turbocharger, but if I have a large turbocharger, then I will have some trouble at low end torque, so basically it's not possible. So what is important, another important area is the low end torque and mass torque. The two of them are what I call the down-speeding strategy. That means that I would like to have low end torque as much as possible in order to be able to increase the first gear ratio. Thanks to that, I'm able to do the launch up and to have a right tipping. And so that's one way. And if I have more torque, perhaps I can increase the second and third gear and then to have a down-speeding strategy for max torque. So I'll explain why valve leak and turbocharger are so important. Now I'm going to describe what we do on our two last engines. So what is called the TCE 115 horsepower and the TCE 90 horsepower. So these engines are a 4-cylinder engine, 1.2 liter GDI with 2 VVT, and the other one is a 3-cylinder engine, but MPI and only one intake vac time system. And so I'm going to show you some measurements we have done and some analysis we have done in order to emphasize why it is so important to have VVTs on turbocharger. Okay. Now, so as it has been explained this morning, one interesting thing to do with VVA is to reduce the pumping losses. And so I'm going to present you another way of VVA to reduce pumping losses, but the consequences will be exactly the same. Here is what we call an electrical driven waste gate. That means that with such a device, so the waste gate is the control of the power of the turbine. If it's electrical or if you have a vacuum pump, and you are allowed to open the waste gate at partial load. Basically, most of our gasoline engines are just controlled by the pressure we have inside the intake manifold. So we are not able, basically, to open the waste gate at partial load. So that's a trend we have in the market at that moment, that most of the new gasoline engines have a waste gate that can be opened. Here you have the pressure. So in straight line, it's the pressure in the intake manifold with different BMP, and in dashed line, you have the consequence in terms of pressure before turbine. Of course, every time when the wastegate is open at partial load, in fact, you will adapt the pressure in the manifold, but you will not have an effect on the turbine pressure before turbine. It was not the case when we have usual systems, because every time we have to increase the boost pressure, so it's below 10 bar of BMP for me, the limit where I have to begin to boost with a turbocharger. So that's more or less the natural respiratory area. I have an increase of the pumping losses. So that means that during this sweep of BMP, in one case, the pumping losses is reduced, and in this case, it's still more or less constant. So, of course, it will have a bad impact on the BSFC. And so, we can say that's marvelous, we have to implement that. Of course, perhaps it's a little bit more expensive because the actuator, an electric actuator is obviously more expensive. If you have to add a vacuum pump, it's also more expensive, but you have some benefits. We have to take care, and it will be the same with the variable valve timing system, but in the meantime, the turbo speed is reduced and gravity reduced. Here we can see that basically here we have 60,000 RPM with a closed turbine, and with the open one, we are less than 20,000 RPM. The consequence of that is the transient behavior. The transient behavior with, I would like to say, an optimized pumping losses. But just an example, but VVA disaggregation system, we have the same trouble. If you apply a VVA system with a turbocharger system, with a turbocharger, you will have a decrease of the enthalpy before the turbine, and due to that, you will begin your transit with lower speed, and you will reach the boost pressure smoother, with a delay. And so, it's one of the drawbacks of all these systems is that we have to take care, with the turbocharger, we have to take care about the transients. Otherwise, as I have said, one way to improve the fuel economy of the vehicles is to have longer gear ratio. If you have some trouble in terms of transit, you will shorten a little bit the gear ratio of your powertrain or of your drivetrain, and so you will lose a part of the down-speeding strategy. To overcome that, what we do on our engine is to promote the scalaging. So first of all, I will show you what are the impact of the scalaging in a four-cylinder engine that is perhaps a more difficult engine we have to work with. And then I will move to a three-cylinder engine. Basically, when I have no variable valve timing, I need to have quite a small scalaging period. So the overlap has to be reduced, otherwise the idle is not stable. So here you have the pressure traces at the intake in blue, red it's the exhaust, and within the cylinder for two engine speed, 1,500 RPM for low and core, and 5,500 RPM, so high speed. And so what you can see is that basically during the overlap, the pressure before turbine, or the pressure at the exhaust, is far higher than the intake. So that means that the scalaging cannot occur, and what you do is backflow. And it's even if the mean boost pressure is higher in the and is higher than the mean exhaust pressure. So that means that the scavenging is not possible in that case. At high loads, high engine speed, basically the pressure before turbine is too high, and we have to the difference is too high, so we have to decrease as much as possible the scavenging. Otherwise, we have some issues in terms of combustion stability. So, what we do in order to not to have this bad situation is that we shorten the exhaust valve duration in order to launch the exhaust blowdown later in the cycle. And of course, it will have a drawback at high engine speed, because if you have lower exhaust duration, you will have some difficulties to push the exhaust at high engine speed because of permeability issues. So basically that's how it works, all 4-cylinder engine with no VVT. The interest of having just a VVT at the exhaust is that you can move your blowdown and this peak of pressure away from the bottom dead center. And thanks to that, we are able to have a positive pressure between the boost and the exhaust and in the middle of the cylinder. And so we are able to do some scavenging. That means that we are able to have air that intake air that push the exhaust to the exhaust side, and it can be shown here with the traces of mass flow rate through the exhaust and the intake. And you can see that in that region we have, through the scavenging process, we have an increase of the mass flow rate at that time. And so, and if I go further, that's so in dash, that was the previous setting of the valve time. I push on the right the exhaust curve, and then I have more possibility. Of course, I will increase the overlap, but I have always a situation where I have some scavenging and I can have more boost pressure, more mass flow rate. Thanks to that, here you have some maps with intake valve actuation, exhaust valve actuation at 1000 RPM. So you can do with you can play with your two VVTs on this 4-cylinder engine, and you can see what is the sensitivity of volumetric efficiency. In that case, I speak about the volumetric efficiency calculated in the intake manifold condition, not in order to not to take into account the effect of the boost pressure. So it's more or less the volumetric efficiency in a situation you do not have the turbocharger. So what you can see is that if I come back to the position where I do not have any VVT, so this one, I can move with the two of them, I can move to this point. And what you can see is that in fact I move from a situation of 0.7 volumetric efficiency to a situation of something like 0.9, and sometimes it's better than that. It can be 0.95 or something like that. And so we have an advantage now. We have a big advantage to change the exhaust valve timing, but also to change the intake valve timing, because retarded valve timing position of of the intake leads to late intake valve closing, and when you have late intake valve closing, you have a lot of backflow at the end of the intake phase. At the same time, if I have a look on the boost pressure, that means so that's what does the VVT. Here is the interaction of the VVTs with the turbocharger. And what you can see is that the turbocharger, even at this very low engine speed, 1000 RPM, it's really a tricky operating point, but very important for launch. What I can see is that I can increase the boost pressure from something like 1000 millibars to 1000 and perhaps it's more than 1020 or something like 1120, something like that. So it's more or less 10% more of push pressure. So it appears at very low engine speed you have more even if you increase the engine speed. And so it's another way to increase it, because here I can have, with the volumetric efficiency, I will have an increase of the torque, and the boost will give more. And at the end, if I look at the sensitivity of the torque, with regards to the back timing, we can see that with only intake valve actuation, I can have perhaps 1.05% ratio, so that means 5% more of boost of torque. But if I have the two of them, I'm able to reach something like 20% of improvement of the torque. So that means that just with two VVTs, you can increase more or less your sensitivity of displacement of 20% in a downsizing project. So that's a lot. Of course, I have spoken a lot about the synergy between the VVTs and the turbocharger. I can help this process through the turbocharger also. What is well known is that I can use a twin-scroll turbocharger. Basically, a twin-scroll turbocharger is here to increase the capability, not to have this interference between the two consecutive cylinders. So it's very efficient, but unfortunately, for Renault, we have another problem, is that we are designing mostly very small engines, affordable engines. And that means that we have difficulties to implement twin-scroll in our engines because of the difficulty of the process. It's very difficult to have this thin separation wall up to the score, constant with a very small turbocharger. And so what we developed, I have seen in the chart of this morning that Audi, it was a turbocharger coming from Audi, but there are others who are working with the same direction. For small turbocharger, what we do is to implement a separation wall. But inside the exhaust manifold, and it gives us a big advantage as a VUC. So basically, that's the situation I presented before. We had just a small problem there. So that's at 1,500 RPM. Here is at 5,500 RPM. We have a previous situation with no VVTs, with a separation wall. What you can see is that we can decrease this peak of exhaust pressure, so we increase the capability of scavenging thanks to that, and more perhaps at 500 and 500 ppm, 5,500 ppm, we are able to eliminate more or less this peak during the scavenging. So even if at max power we are able not to have the backflow or to reduce the residual gases. Just this simple change of the design of the exhaust manifold, we have been able to demonstrate 2 or 4%, depends on the engine speed, of torque, thanks to that. So it's just a small modification. Nevertheless, we are sure that we are not optimized. And if I come back to the transient, here you can see the benefit in terms of transient of the interaction between turbocharger and VVTs. Here you can see that with no VVTs, the transient is very poor. You can see that on the BNP. We have the level, of course, as has been described before, is low, and the turbocharger speed, and it will be the same for the boost pressure, is increasing very smoothly. If I have just an intake manifold, of course I will have a benefit in terms of torque, thanks to the early closing of the intake, but and I will have also better transient, but not so much. If I have both, as you can see here, it's another engine, and in terms of transient, it's another engine. So there is a huge synergy between VVTs and turbochargers, even in transient. But it's in fact the most important, because it's not fair to have it's not a for us to have maximum torque in 10 minutes. I have some examples of two-stage turbocharger where I reach the maximum torque at low end torque in 10 minutes. It doesn't matter. I do not use it, because in real life in a vehicle you have to have the torque in 1 second, 2 seconds at least. So the transient behavior is really now, and even more you go in the downsizing concept, the transient behavior is really, really something you have to take care. A difficulty nevertheless, and I know that there are some tuning people here, is that you have to know the track in order to adapt exactly what must be the injection timing, the injection duration to put the right quantity of fuel, and to know the right ignition timing. And it's not, the problem is that during the transient, the volumetric efficiency is not the same as in steady state. And so you have to take care about the correction and to know where you come from in order to know this track air mass flow. With a 3-cylinder engine, marvelous engine for gas exchange process engineer. Because basically, if I come back to this, to this chart, the situation is naturally the best one. In fact, due to we have an exhaust blowdown every 240 degrees C, and the overlap is at 180, and so we have always a positive situation in 3-cylinder engine. So that means that we can allow a lot of overlap, and we'll have a good impact on the turbocharger. Nevertheless, even at high engine speed, so it will depend on the maximum power, but kilowatts we have, it's the situation. We are close to be in the situation where during the scavenging we are close to have the exhaust pressure close to the intake. So that means that sometimes you can have scavenging even or close to the max power. That is quite strange. Even if the mean exhaust pressure is far higher than the mean boost pressure. So that's the advantage of three-cylinder engine, and that leads to less residual gases, and thanks to that, better efficiency. Nevertheless, in transient also, it's just with an intake valve closing, intake valve VVT, because it's the only one we have, we can see that the difference of torque is increased due to the scavenging process. So it's an advantage of a three-cylinder engine. And but we have also the same trouble with the truck mass flow rate. Nevertheless, I have a problem with this engine. I cannot scavenge as I would like to do because it's an MPI engine. And here you can see what happens at 1500 RPM when I do the intake actuation at a constant BMEP. So every time I control the booster with the actuation of the wastegate. And here you can see that if I do too much scavenging, that means I increase the intake actuation. I will increase for this high loads a lot the BSFC. Of course, through scavenging I can have right efficient volumetric efficiency, but I will have a drawback with the BSFC. And basically, it is due to the fact that the scavenging is done with air plus fuel. That is shown here with the HC content of at the exhaust. And so, with the MPI engine, you have to take care about this scavenging process. You have to, perhaps you can allow it in order to, for fast acceleration, you can allow it in order to have a feeling of a big engine. But you do not have to put it in place too much time, otherwise the customer will see something on its fuel consumption. Okay, just to conclude, we have seen that for these two agents, the scavenging has to be promoted, and it's natural for three-cylinder engine. It helps us a lot in terms of steady state, but also transient. And there are some limitations with MPI engine. And at the beginning of the presentation, I have shown you that VVTs, it has been explained this morning, and open wastegate can be solution to decrease the pumping losses, but we have to take care about the transient and the bad synergy, in fact, with the turbocharger. Now, if I try to summarize what will be my recommendation around the setting of a variable a VVA system, so fully VVA system with the possibility to change the duration of the exhaust and intake phase. I would say that basically at high engine speed, with a three-cylinder engine, I will require larger duration than with with a 3 compared to a 4. Basically, what we do is to increase the take-back closing in order to have some profits of the weight propagation inside the cylinders, inside the deck lines, and due to the compromise we have to do between expansion stroke and pumping losses, I will have to increase a little bit the exhaust valve opening. In 4-cylinder engines, due to the fact that I will have this interaction with the blowdown of the consecutive cylinders, I will have a little bit to reduce the exhaust valve opening. So I will decrease the duration with the speed, and during the scavenging, I will be able to perhaps to have a demand of more scavenging with a 4-cylinder engine than with a 3-cylinder engine, because of the fact that naturally the 3-cylinder engine promotes a lot the scavenging. So we do not need to increase too much the scavenging. And at low engine speed, there are some small differences due to the fact that there are less residual gases with a 3-cylinder engine than with a 4-cylinder engine. And we have to reduce a little bit the duration because of the pressure, and due to the functioning of a turbocharger, we have less pressure, so the potential of scavenging is lower. So we can use a large overlap. And finally, perhaps I know that there are some professors here that are perhaps sometimes looking for some research. So just to 3 topics I would like to perhaps address you. First of all, what is not well known, basically, is the right balance between the steady state BSFC with all our systems, the potential of improving the steady state BSFC and the transient behavior. And I think that that has to be the control, otherwise it will not be will go into direction that we cannot implement in the real world. The word separation between of turbine housing for small turbocharger is really, I think, it's really a topic that we have to work on because basically there is a huge constraint in terms of thermomechanical in the turbine housing, and we have to work on that in order to improve this separation effect, and especially at low engine speed. And for tuned people, I know that it's really tricky to estimate during scavenging the air mass flow and the trapped air mass flow, and it will be critical in the future because I don't know where. I know that the discussions are not finished, but there are some assumptions to do some tests in real drive emission to homologate an engine. So that means that a driver will take the engine, go on the street, on the back he had all the system to measure the pollutants. And if we are not able to know precisely this kind of the trapped air mass flow and the fuel mass, that means that we produce a lot of HC, we produce a lot of particles for GI engine, and that will kill all the systems we try to put in place for scavenging. So I think it's a key point for the future. Thank you very much. If you have any questions.
before I forget, I have one question, but before I forget, I want to announce all the people here that the Romanian Society of Automotive Engineers, which patronate this event, will organize presentation of the move system of AVL. You mentioned that in the near future we will need to put measurement, emission measurement equipment in the back of the car, and afterwards to see what's happening. So that's, before I forget, it will be after the Easter, on 8th, Stefan, on 8th of May. And we will send all the information to Renault and all the other university. The Polytechnica University of Bucharest will be the host. So, excuse me, but I wanted to do. I have a question. Can we apply double VVT in extreme downsized turbocharged diesel engine? Because with the diesel engine we have, with the extreme downsized diesel engine we have problem with transit, and I suppose VVT could help.
In fact, not. Fortunately not, because basically the diesel engine, the intake closing is quite early, and the exhaust pipe opening is quite more or less at the optimal position. The problem you have it's not a problem. The situation of the diesel engine is that we have a high compression ratio, and we have to avoid any impact on the pistons. And due to that, the overlap has to be reduced as much as possible. Not as much as possible, but has to be reduced. And so the possibility to increase the overlap is very, very small. So, of course, you can go in the direction of increasing the, for instance, the intake. Yes, I can increase the intake by closing. I will have no issue with, but it has no interest for high speed because the speed of the diesel engine is not enough. And so, basically, there is no interest of VVTs in diesel engine except for soot or something like that, so pollutant emissions. But for full load and transit, there is no interest.
If you allow me another question, that's slide number 7, Stefan. I don't think I understood. Say by the way. You were talking about avoiding thermal load on the exhaust side, and you wrote early exhaust valve opening right there, and I suppose it's right in the sense of if we open earlier.
In fact, I will have less pumping losses at that engine speed, and thanks to that, it will be beneficial for the PSFC. And then we'll have to shut it off. So then I will have an increase of the temperature.
So it's an increase of.
If, in fact, with part of the pumping, if I do, or if I do the contrary, if I do a late valve closing, it will be interesting for the temperature before opening the valve, for sure. So you will have a decrease of the temperature, but after that, you will have some difficulties to push the exhaust. So the mean temperature will be higher. So the beginning of, I agree with you, the beginning of the temperature of a blowdown will be beneficial, but at the end, during all of the exhaust phase, as the pumping losses will be higher, you will have higher temperature. So for the enrichment, it's not the right direction.
I think I understand. Thank
Okay.
you. Thank you.
Yes, sir, please. Tell me, what's the maximum temperature that your turbine of your supercharger system could work?
It's basically 980 degrees Celsius.
Please?
980 degrees Celsius.
Maybe two questions. One is linked to the question which has been asked. The first one is, you mentioned it's not necessarily, let's say, positive to have variable valve timing on diesel, but there is one on the market. Is it linked to the fact it's an electric one, or is there other option, other interest? I mean, I'm talking about the Mazda Sky, I think.
I think it's for pollutant. They are using that for decreasing the
Is it not the reverse, in fact? Are they not using the variable valve timing for increasing, for having some point where they increase artificially?
to increase? When
I mean, they are working with globally with a lower compression ratio, and they increase it. No, they cannot. No, I don't know.
I don't know.
No, I don't understand exactly why they are the pollutants.
Perhaps I have to study more this engine because I do not.
And the other question is, what about the three-cylinder with WLTC and RD? Do you think there is a real potential for such very small engine?
Yes, for sure.
Because you are outside the optimum point.
I think the RD and WLTP will change a little bit the right side. That means that basically perhaps we'll move to higher displacement a little bit. But I would say that the downsizing effect will be kept. So we'll still stay with the turbocharged engine. Perhaps we have I can begin to see that on the market. The displacement is decreasing a little bit due to the fact that with the claim of the customers and after WLTP we have to increase the downsizing effect has a bad, at the end has a bad effect on the real fuel consumption, for sure. No more questions? Oh, more questions.
With your permissions, your lecturers, I will send your emails to the audience so that any question that will appear afterwards could be sent to you directly. Thank you, Stefan. It's a tough day. It's a tough day. We still have two presentations. It's right now it's the turn of the ABS presentation. Dr. Hubert Friedel will
Hello, ladies and gentlemen. my is quite slow, and I don't think it will speed up. Before I go into my lecture, I would like to introduce where I personally come from. So most of you know ABL as an engineering company and company supplying and we have basically three business units. From the turnover standpoint, it's instrumentation and test systems. This is the area where my colleague Tehnologie comes from. The second one is powertrain engineering. This business unit is dealing with the services for designing and developing different kinds of powertrain systems. And the third one, last but not least, this is our division dealing with advanced simulation technologies. So, as you know, ABL is dealing with the wide field of what we call automotive activities. So, incorporate engineering, simulation, and testing. So, this is the wide area of passenger car application to racing and commercial activities on the road of the road, so tractors and building machines. And not to forget the very field you find in locomotives, in marine application, and in stationary power plants. So again, to understand my vision, so I'm coming from the passenger car side. I'm dealing with the development of gasoline engines. And ABL is active in more than 30 countries all over the world. So we have offices, representative offices, and the pictures you see, these are the locations where we have technical centers to undertake simulation work, design work, and also some testing work. And the area I come from Austria, from Graz, where ABL has been founded, and where still is ABL's headquarters. Yeah. So you see the computer is still relaxed, and I have to be relaxed very too. So basically I can say nothing more to tell you because my previous presenter did a very excellent job. They told you everything you should know when you're speaking about variable valve actuations. But I'm kidding. I think there's still plenty of topics open. But anyway, I swear we haven't arranged our presentation together. But I'm fully convinced that the sequence, the order of presentations you have been given today is very well aligned by fortunately and due to Adrian's selection. I think the sequence fits very well into each other, and I would like to enter. What I will tell you today, I will start with the market perspective, to give you an overview how technology will deploy, especially how variable valve systems will penetrate into the market. And there is one other topic. This is what challenges will come up with the new legislation and standardization trends. They already have been mentioned. This is CO2 at the one hand as the very hard driver, and then certification procedures also have been announced. This is WLTP, real driving emission measurement, which definitely will drive our business for passenger cars. And I will go into the topic of today, variable valve actuation. So I do not want to spread out all the different possibilities. I have selected 3 examples of application for such variable valve systems, starting with let me say, the common simple one, the Chemphaser. Then I will give you an example of profile switching, which we think is the very most appropriate application for turbocharged gasoline engines. And as the last point, I will give you an example of a quite very flexible variable valve actuation we have utilized in the CSI engine. CSI means compression and spark ignition. So compression ignition for gasoline means HCCI combustion, so homogeneous charge compression ignition. I think you're very well aware of. And I will conclude with a summary and then outlook. Let's go into the market survey. So the chart you see over the years, what is the number of engines produced for passenger cars all over the areas. And you see, 2012 this line. In the, let me say, Western world, we see a certain stagnation. This is valid for Western Europe, United States, also North America, as well as Japan. The big growing areas you see, of course, this is Asia. On top of all, of course, this is well known, is China, but also what may be seen as very positive to you, this dark blue area. This is, we call it Eastern Europe, so including also the states of the former Comecon, also Romania is in this. So these countries are forcing to have a quite substantial growth in automotive production, also in the near future. A company like AVL, of course, is interested where the business takes place, but to a certain extent, we are also very interested what kind of technology is requested, how the technology mixture deployed over the world. And what you can see, so it's the same number, so 80 million passenger cars engines produced in 2012, last year. 1/4 roughly is diesel engine. This may surprise you because this does not reflect the European situation, because in Europe the half or even more than the half of engines produced are diesel, but on a global scale it's only 1/4. The rest is still, I do not have to say gasoline. These engines have got a spark plug, including here the somewhere in between this orange part. These are the hybrids, which slowly deploy. The yellow one, these are the engines driven by gaseous fuel, so e-fuel, compressed natural gas. The green one driven on alcohol fuels, so mainly these engines are produced in South America. And then the majority you see below, these are the, let me say, the conventional gasoline, but having a very big growth now in GDI, in gasoline directly injection. And what is also very remarkable, what you see on the bottom, turbocharging. Turbocharging for gasoline engines, this is considered to be the main trend what we experience now, especially in Europe and all over the world. One point not to forget, this light blue area, this is electric mobility. Back the last few years from a publication, there was an extreme pressure build up So the expectation for electric mobility were extremely high. So everybody of us expected tomorrow every third or second car will be e-mobile, but this takes time. And then coming back to the GDI, I remember very well in the mid of the 90s when GDI technology swept over from Japan to Europe. There was really, all the people were excited, GDI, now this is the big challenge, this improves everything. But what happened? Nothing. This engine has to be developed, you have to address to clients. The clients some were not convinced at the first time, and it takes a certain cycles of buying a vehicle until a certain technology comes really into the market. And you see here from the mid of the 90s, this is nearly 20 years that automotive technology needs to deploy. And maybe I'm not able to predict it, but maybe also for electric mobility, it will take at least 10-15 years until we have a certain penetration for this kind of technology. All the text you're reading in the slides here also, there's some conclusion between the chapters you can read afterwards when you receive the answer from having some closer look into the individual areas of the world. When we look to Europe, this was already pointed out, Europe is still sticking on diesel. So half of the vehicle population is still in diesel powertrain. The other half is gasoline, and the technology is in between deployed. If we look to China, for example, this country still sticks very, very tough to gasoline engine. It's not a matter of availability of technology, but don't forget one thing. It's not only the passenger car who uses diesel fuel, it's also marine, off-road, the trucks, the commercial activities, and things like that. And the refinery industry somewhere is running out of diesel fuel. This is maybe also some driver why you see for a passenger car that big amount of gasoline engines still over the world. The specific situation you have in South America, they're utilizing biological fuels, ethanol from sugarcane and things like that. This is the reason why in this area alcohol to up to E100 to 100% concentration is in the market. Japan and Korea, probably the mindset and maybe some automotive philosophy is somewhere different. Since many years they're sticking on electrification, on hybridization. Toyota in the last years has made very good progress and made very good business. And if we look to this, if we look to the overall big picture, the hybridization still, or the majority still comes from Japan. Europe is following, but as I mentioned, probably this will take some years. But the expectation of you probably what's about variable bulk system. So I already announced this big picture to you. This picture reflects what is currently on the market and what is forecasted should be. You see here the number of produced gasoline passenger car engines. roughly 10 million of units. 10 million gasoline engines produced in Europe. And the gray bars you see, this is the one who does not have any variable system in the valve train. So this is like a conventional stiff valve train and no other flexibilities. You see, such engines having no UPIT system are definitely fading out. When you split down to the different technologies, I start from the top with the red one. They're called valve lifting. So I took these definitions from IHS. This is a company which is providing this data. Cam lifting only means this is a variable system, only having a full variable valve lift. So this is the uni-assist system. And the red bars, or these red slides, they're definitely probably all the engines produced by Fiat. The green ones, they're called cam changing only. These are the system who are able to switch only the lift of the valve, but no phasing in between. This is probably, or maybe something surprising, because these are mainly the Honda engines. There are some Honda vehicles built in Europe, and therefore they are included into this statistic. This is the Honda VTEC system. You probably all know. It's a system holding the finger follower of the system. The light blue bars in between, these are the engines having at least one cam phaser. This is the majority of the gasoline engines. And coming down to this darker blue area, it's called cam phasing plus valve lifting. This system, the majority are the valvetronic systems in the BMW engines, as well as in the Prince engines, which are commonly produced by PSR and BMW. So these are the engines of some Peugeot vehicles, but mainly the Mini Cooper engines. For this technology, I see, so I interpret myself, variable valve system maintaining somewhere stable. But on the other hand, if you look to this dark blue, this is cam phasing, cam changing. These are systems like the system Mr. Golovati has explained. This is the system with this shiftable blobs. And if you ask me honestly, this is also ABL's view that such a simple system has the most promising future, because it's not only a matter of flexibility a system can offer. What you have to take very carefully into consideration is the power demand. The power demand and also the control demand for such a system. This has to be always balanced very carefully with the potential benefits to the game. This is the Europe situation. If we switch over to Japan, maybe this is not so surprising to you. Japan, since many years, they are promoting cam phases and valve grid system. You see the area of the gray bars, which do not have any system, is much lower than in Europe. So each or most of the Japanese produced cars have a cam phaser, even the very small engines. But from the diversity of technology, you see valve lift. No red bar. sorry. Unia is not yet available in Japan. I was surprised that they were. The green one came changing. This is the Honda engines. Majority having 1 or 2 cam faces. And look to this cam facing valve system, fully variable valve system, also expected to maintain a certain level, whereas also here the cam changing, so switchable devices are expected to get in bigger numbers. The figures you see here are quite very reliable, and I call it, these are hard numbers you can rely to a quite high extent. So, coming to the second topic, the challenges we see from upcoming regulation. This is probably not, let me say, the hardcore topic or the hard topic for variable valve train. This is probably much more a topic, as you has already addressed, GPI and turbo. This is the technology which even have to suffer much more from the upcoming regulation. Variable valve actuation, I may say, they still can maintain very fine also with the new regulations coming up. Similar picture like that you already have seen. CO2, this is definitely the hardest driver of all. All the other challenges we can meet, but CO2, this is the hard driver. And you see the progress of CO2 emission of the overall fleet, how it went down in the last year. And the red and the green line you see, this is the average of the diesel engines and the gasoline engines. In former times, the diesel engines were very much ahead of gasoline. In the last year, they have nearly touched. So I could say gasoline engines did such a great work, they were able to improve that much more than diesel, and diesel still are not that fuel efficient as they have been. Oh, I'm kidding. The diesel definitely will maintain the backbone to achieve the CO2 targets in Europe. The reason why we have this situation is different. I will show you later. But shortly, we are definitely, or the industry is definitely convinced to meet the targets for 2015. For 2020, I think this is a quite gap, and you already showed it in your graph. Without e-mobility, probably this will not work. How it will work, I do not know. I am not able to predict. But coming to this situation, you have to see some fact. The population of vehicles in the market, you can distinguish between small vehicles and big vehicles. You see here the segmentation, the A-class, A, B, C, D, E-class. A are the very small cars, the compact cars, this is the Golf class, this is the dominating class. Then medium, Audi A4, Passat segment. I've included the mid-turbos vehicles, and of course the premium segment, including the heavy SUVs, can be seen separate. To give you the answer of the question before, why is gasoline that close in point of CO2 emission? The solution comes out from this, because the small segments, the A-class vehicles, are dominated by gasoline cars, so they are fuel efficient anyway. You see this segment, the very small diesel share, whereas with the more higher weighted classes, the diesel share increases, and they of course have a higher CO2 emission. This is the reason why these curves came together in the last year. And this is also the expectation for the future. So the big and heavy vehicles also in the next year will be dominated by diesel technology. So it, I think everybody of you knows, the more the vehicle weight, the higher the fuel consumption. If you look at the landscape CO2 emission over the vehicle weight, you see the dots. So the gasoline vehicles naturally aspirated are still ahead of other technologies. This is valid for Europe, where we have to meet this blue line, as well as in China. You see this red stamp line. So for the naturally aspirated gasoline engines, there's still a wide way to go. In that respect, variable fluctuation can contribute quite much. According to the trend, these blue squares, these are the representatives of turbocharged gasoline engines. They are already somewhere ahead of the naturally aspirated gasoline engines and expected to follow on. And you see also quite a good number of these turbocharged gasoline powertrain which already undergo the target line. As already mentioned, the world of CO2 reduction will not work without hybrids, and the yellow dots, if you see this kind of vehicle already nicely below this red line, or at least close to it, and they will proceed even, especially when you consider plug-in hybrids and things like that, where you can run much long distances purely on electric. And there is one more argument. If you look to this red triangle, significantly below the target line. These are the vehicles operated on CNG, on compressed natural gas. And please bear this in mind, compressed natural gas is a very attractive fuel, not only from the properties due to the knock resistance and things like that, but by the nature of the fuel, the share of hydrogen to carbon is that positive by using methane instead of gasoline. You have nearly 25% benefit in CO2, the same power more or less and things like that. And this probably will come into the game even much more in the next years. From the pollutants, we see year by year, over a few years, we have even more tough regulation, more stringent regulation, including on water diagnosis and things like that. This is definitely a very hard task, but we have learned to live with it. The highlights in this evolution of legislation for the diesel, it's definitely NOx. So the diesel, this is the big challenge for the diesels to meet the NOx targets. The particulate topic has been solved by introducing a particulate filter. This is no more a worry. And for the gasoline engines, as you know, more and more GDIs coming into the market. The particulate number emission, this is the core target. Even we have learned to deal with this subject we have made significant improvement in refining the combustion system and things like that. We're still working to provide a certain stability of the emission levels and things like that. We are absolutely confident by technical means it's possible to reach even the other limits of particulate number. But if you ask me, it's quite probable that also the gasoline engines will end up with a particulate filter in the next years, not from a technical standpoint, but maybe from a marketing standpoint. So, here this is one chart my colleague already has spoken about the upcoming regulation. So I do not want to go in detail. The NEDC, the new European driving cycle, dealing mainly with CO2, will potentially be replaced by the world harmonized light duty vehicle cycle, which we already is more aggressive, has a higher load and things like that, more dynamics. If we think for variable alpha calculation, the systems have to deal with this more aggressive cycle. But the main challenge probably comes up from RDE. RDE means real driving emission. So this is really the European community and the legislation, the government, they will have a close look what will be emitted in real life, not in the nicely tuned test cycles, but what happens in real world. As I say, also the customers do not want to be cheated anymore. They want to make it proof. And you see the comparison of the world harmonized cycle in the NEDC cycle. So the acceleration is more aggressive, the average speed is higher, the load is higher. Basically, we expect this will end up with more or less the same CO2 emission, even to this other challenge. But again, depends. The portable emission measurement system, this will come into force more and more, as Adrian already announced. We will prepare a demonstration for such technology on the market. So as ABL has not promoted this technology, this definitely comes from the European Commission. The automotive industry also proposed an alternative to make this random, this real-world testing on test facilities by means of random cycles. As far as I have been informed, this idea is deleted somewhere. Of course, it will be done, but this will not have that relevance in the future anymore. And here, to explain what happened, so you have already seen it before. This is the borderlines, so the performance line of the vehicle. Usually, vehicles are nicely treated into this new European driving cycle area. The industry committed to say, okay, we know in the area close to full load, there we have to apply improvement and things like that. But the European Commission says we do not want to have somewhere a selected area. We want to have possibility to test all the conditions which may occur on public road. Going the hills up and down, accelerate, drive hard, drive smooth, in congested area, whatever. And the real driving emission only may exceed the certification levels by a certain distance. So, as here still active. Now coming to the topic of today, what's going on with variable valve calculation. And from a general technology perspective, you see in this slide, it's not only the engine, it's not only the car, it includes the tires, the wheels, the fuels and whatever. Each small contribution we can gain to improve the fuel efficiency will be drawn out, so this will not stop. And if we look to gasoline engines technology, starting from nicely refining the combustion system, so still a lot of progress is going on in this respect. We have heard a lot of variable valve actuation systems today. This technology can contribute significantly. It's turbocharging, very important, downsizing or what we proposing, right-sizing the engine. We will have cylinder activation to a much higher extent. So in former times, cylinder deactivation was only dedicated to 6, 8, 12 cylinders. Now we go down even from 4 cylinders, we are able to shut off 2 of them. So the progress is happening on, and of course complementary measures like hybridization, exercise cooling, and also the traditional crank frame probably will change in the next year. So the crank consisting of the piston, the control, and the crankshaft probably will be replaced by a much more complicated system. So you can see here, this is the example of the French MC5 engine, featuring basically variable compression ratio. But we will see definitely much more advanced systems also from the mechanical side. So progress is going on. Of course, the innovation and the introduction of the different technologies, this will not go by one shot, so it will go stepwise. So we really collect the contributions of these different technologies. So when looking to cam-facing, cylinder deactivation already is somewhere introduced to the market. It will go on. GDI, turbocharging, the same, well established, making the progress. Followed by a certain kind of hybridization. And you see the following. So we will have cooled EGR. This was a question of today. Why to have an external EGR system? So we really think about extreme high EGR rates and to feed really an enormous amount of cooled EGR. And to cool the EGR, you really have to pass it by over a cooler, and we are not able only to internally recharge it via the valve train. The stratified GDI engine probably is a niche, so Mercedes still sticking to this technology. You have to bear in mind, due to the exhaust after treatment, still quite very expensive technology, and it's probably a niche. I have spoken about variable compression ratio, variable expansion, by mechanical means, not only by the cam, by the valve timing, but really by mechanical means. We will see. And I do not know when, so we're speaking on that so many times that we have heard today. HCCI combustion, alternative combustion technology basically is available, but I do not know when the first will be to introduce this technology in the market. And of course, hybridization mild, full electrification, whatever, having range extender and things like that. Step by step, this technology will come to the market. Speaking about the variable valve actuation system, you see the three representatives. I do not, after my presenters up front, I do not have to explain the pictures anymore. I only want to highlight, bless you. I only want to highlight the examples I would like to give you. For the cam phaser, I would give you an example of variable charge motion and cylinder deactivation. This does not directly link together, but I want to explain you the complete story. I think in this respect is better understandable. And I would like to speak on charged GDI engines. That's already now controlled auto-ignition. Starting with the cam phaser, the system, we call it CPR, controlled burn rate. This is quite an old story, but still modern and still active in the automotive industry. The trick is you have a certain kind of shape of the intake port. You have a tangential port and a neutral port, and in the first case it was possible to shut one port. This also can be done by means of not opening the valve, for example, but this is one mechanical means to close the intake port. And when you have the complete intake airflow over the tangential port, you see here you generate a very strong charge motion. But the charge motion itself doesn't help you, because to have a high charge motion costs energy. The movement of the air costs energy, and this would basically deteriorate the fuel efficiency. But you do this because in such a stable condition you can really pour a lot of EGR into the system. Pour a lot of EGR into the system, de-throttles your system, you can open your throttle wider, even maintaining the power, and this at the end gives you the fuel benefit. And in the CPR of the first generation, we utilized it by an external line for EGR, and the second generation of CPR, we utilized the cam phaser to bring in the EGR by internal means, so directly from the exhaust. And the examples quite with the engine, but this technology already has been in production for a long year. So this was the Opel system, having a mechanical port activation by flat. So this technology was built in many millions of units, and the CPR generation 2 was adapted by Fiat, having a slider instead of the mechanical butterfly valve, and utilizing already a cam phaser for internal EGR. When looking to the core components, so for the generation 1, you see you have, it's not complicated, but you have some mechanics to operate the flaps. You have an external EGR line, EGR valve. Nobody really likes EGR valves. They may stick, they can corrode and things like that. It's one piece more, nobody likes it. In the second generation, like Fiat did with the cam phaser, much more attractive component, much more reliable from a cost standpoint. It's the same, but it gives you much less headache to have such an equipment. But even in that configuration, to have this slider, the slider may stick and things like that, these are the ugly things, and we worked on it to skip it. And the current technology we call CPR of third generation. We are rid of all these mechanical parts. We only use one single cam phaser, but you may ask, where does the charge motion come from? The charge motion comes from a specific design of the ports and having specific masking at the valve seats. This at the end gives you the charge motion. This CPR technology applied, we call it, it's a correct naming, Blake Atkinson cycle. You already heard about this, how this works. Green line is the top dead center, and we retard both the exhaust and the intake to lake. This is the trick. And due to the fact that the exhaust valve still is open, when the piston already goes down, you draw in exhaust direct from the exhaust port. So you repress the exhaust, hot exhaust. In that case, the part load is not so bad. Then the intake valve opens, and then you have the natural stroke of aspiration, where from the intake fresh air comes in, but you arrive at bottom dead center, and you see the intake valve is still open. What happens? So if you proceed on, you move the piston back, you have a quite substantial shift of intake air back again. This is a measure to reduce the amount of burnable charge in the combustion chamber. So you only leave that amount of burnable fuel air mixture into the cylinder what you need to run a certain power. And this, at the end, this brings you the big benefit. You can operate the engine in that condition more or less unthrottled. So you really, in such configuration, if you have the appropriate combustion stability, you operate, you do the load control only by means of the cam phasing. I'm coming back to the generation of charge motor. I think it's better to be explained on a two-valve engine. You see, the intake port, the air is coming in. It's eccentric, and what does suction flow create? It creates a swirl motion in the cylinder. As I've explained before, but also the exhaust port stays open quite long, so that gives you a reflow of exhaust gas, and additionally to the charge motion of the intake air, the returning exhaust gas supports this swirl motion. And this at the end is a very strong charge motion. And you see here, this high charge motion is an enabler to run the engine with a very big amount of EGR to de-throttle the engine. And you may believe it or not, such a principle since many years, so Giovanni knows it, since many years, this is quite successfully in the market. But such a system is not the one you can highlight in advertisement and things like that. let me say, these are the silent servants who do the job and improve fuel efficiency. But probably it's too less spectacular to be announced. But these are the simple things you can do with that kind of cam phaser, and I think this is even worth to be pointed out. And that system, you see, we do not need some port activation or some other mechanical device. We generate the swirl or tumbler by the intake port and the exhaust port, in addition with a smart masking of the valve lift. And at the end, such a simple system gives you a benefit of 3 to 5%. And we consider this as a kind of, we call it, this is really smart simplicity. Also what you hear in the later presentation, there's always, how to say, the motivation of AVL not to present something highly spectacular and things like that. So we would love to do this, to do the crazy things. Of course we do many crazy things, but at the end, when the customers come to us, they say, okay, I love your crazy ideas, but can I have it cheaper, at least half the price? And this motivates us to do the simple thing, but of course trying to utilize the benefit as much as possible. I come over to the point of cylinder deactivation. We also have heard today there are different kinds of cylinder deactivation already available on the market. So the systems, you know, usually work by completely closing the valves, and the cylinder is working as an air spring. These are, of course, the systems which provide the highest benefit with respect to fuel efficiency. You see the examples of the Honda utilizing the VTEC system, and the newly introduced Volkswagen system using this sliding block system, which is quite very successful introduced into the market. But again here, AVL is forced to do the simple things, and AVL presented a kind of cylinder deactivation, but without any mechanical means. So purely shutting off the injection. You may say, this is so simple, why nobody else has done this in the past? You're shaking the head, but it definitely works. And you have to understand, it's not only a matter of switching of the fuel. You have to do some complementary things, so I will explain. To understand better, I give you the example of the V6 cylinder engine, because the 6-cylinder engine has got two individual banks, two individual exhaust systems, and therefore it's even easier to split the system into two halves. What are we doing? We shut off the injection of the right bank, and we do the cam phasing shifting to late position of the cam phaser gives you minimum pumping losses. This is one argument we are playing. And the other bank we keep firing. We have to inject roughly twice the amount of fuel into these cylinders. So the remaining cylinders have to do the job for the others, so they have to work harder. But this is basically the benefit you expected. And the cam timing for this left bank is set to minimum right bank minimum pumping losses, the left bank optimum fuel consumption. The only, again, this is purely electronic, no mechanical devices, with exception of the cam phases, of course. This also works for a 4-cylinder engine. The only thing what you have to do with a 4-cylinder engine, you have 4 cylinders, you can have whether the outer 2 cylinders running or the inner 2 cylinders running. The only thing you have to do, you have to separate the exhaust lines. So you combine the inner 2 cylinders and combine the outer 2 cylinders. So we have done it by means of a water-cooled aluminum manifold. In the separation is done by a wall, so it's maybe that kind as you presented for the turbocharger. You divide the path and lead it until the surface of the catalyst spring. So it's still one catalyst. You have only one separation board. The front side is utilized by the outer cylinder, and the inner face is utilized by the cylinder. This is the only precondition. You have to separate the active and the non-active cylinders from operation device. Gives you 4% fuel economy improvement, and we have applied this to 8-valve engine, so 2 valves per cylinder, having one cam phaser. And what I tell you now is somewhere very similar. I have explained to you up front with the CPR system. So you have one cam phase acting to all the valves, and when you shifting too late to retarded position, you have the effect, as I told you before, you have lower pumping losses, and you get in EGR, internal EGR. When you, so this is residual gas. When you draw in more residual gas, you're reducing the BSUC. So this is due to the fact that you're de-throttling the engine. But you cannot do this to an infinite limit, because the more EGR you bring in, you see here the residual gas content, the more EGR you have, you reach somewhere a point of stability. So you risk misfiring. This you have to avoid. Therefore, you have this limit you must not undergo. And basically, if you only would switch off the cylinders for cylinder deactivation, you would have this limit, and the reduction in fuel economy would not be that high. But you have to see the situation that the other 2 cylinders are working at a higher load, and these working cylinders, due to the higher load, have a much higher resistance against EGR compatibility. So again, this is only the effect of cutting off the injection. But due to the higher load, you're shifting the borderline to outside. And at the end, this gives you that point. You see here also somewhere 20% of residual gas. And at the end, this brings you 10% improvement in fuel economy. So again, it's not only to shut off the fuel, you have to improve the EGR tolerance, and then combining this effect, you end up with 10% improvement in that specific point. only by means of CAN-phaser, no other specific device. So this is what I want to tell you before. The only criteria you have to accept the non-working cylinders. So that you're still pumping air through the cylinders, you must take care that you do not undergo the catalyst temperature, because otherwise you would have some problems with the efficiency. And therefore we call it toggling. So you have to take care for the catalyst temperature, but you can switch over from one bank to other. We have refined it in that way. This is really nicely acoustically treated. You're definitely not able to recognize which bank is active, whether you're running on 4 cylinders or 2 cylinders. And you see there's quite in the DC cycle, there's quite a long time when you can operate in cylinder deactivation mode. So we have, I show it, if it comes up. Yeah. We have adapted this system to demonstrate the abilities of our own activities, and we have demonstrated it already in several project parts of the improvement. This is really approved. For this car, this is a Fiat Punto 1.4 liter. We didn't only add the cylinder deactivation, but we applied some other tools you see here. This picture you know very well. So we have this electronic cylinder deactivation. We did some improvement in the friction of the engine, so some special headlights, a variable oil pump. We applied additionally an electric supercharger from Relay. The vehicle has got an automated transmission, and the target was to fight down below 100 grams of CO2, and for the last 3 or 4 grams we have to fight in that way. We did by kind of an underbody cover, so that underbody that gave us some improvement, so the final improvement in the aerodynamic strength. And finally, by incorporating all these, let me say, tiny measures, at the end we ended up with 100 grams of CO2, which we consider a quite remarkable result for such availability. The end is close. Profile switching in combination with this turbocharged PDI. So, from my colleague Mr. Golvati, you already heard about the pros and cons of different valve switching devices. Also from my personal standpoint, as you see, this sliding lock system probably will prove the smartest systems of how to follow them. And what we already heard today, turbocharging, downsizing, this is the trend of today. And this chart shows you the share of turbocharged engine in the fleet. And on top you see the blue line of BMW. BMW is expected that within a few years, nearly all of the engines of the BMW brand will have a turbocharger. Probably Rolls-Royce engines, they will maintain naturally aspirated, but the mass engines are expected to be purely turbocharged. Audi is following the trend. VW in Daimler also do so. So we may expect that the majority of gasoline engines, especially in Europe, will have a turbocharger. And this, of course, will bring some consequences to the technology. And what we see now, there's not one golden route how the configuration looks like. When you see the torque of the BMW, you see they've applied a twin scroll, so BMW, say, with bigger engines here in the premium class, money cares, of course, but not as much as for other brands. They utilized twin scroll and F-phase intake exhaust, and also BMW has proved to industrialize the Valvetronic system, and they put it on top. So all the good things BMW brand is capable, they do. Audi going somewhere a different approach, so we discussed during lunch. So what the one does, the other must not do due to image reasons or whatever. But you see Audi has a single scroll, of course, intake and exhaust cam phaser, but they're doing the switchover of the valve tip on the exhaust side. On the exhaust side for the reason to utilize the scavenging in a very smart way. Also nice for me, I do not have to explain scavenging, you did it very nicely. But on the other hand, like Fiat Alfa Romeo does, they say we do not want to have some fancy equipment in the valve train. We think the simple single scroll turbocharger intake and exhaust cam phaser is sufficient. And Alfa proved also to have also the same or adequate nice blow and torque characteristic like their competitors by having quite sophisticated control strategy. So this is not driven by mechanics, it's driven by the control strategy of the cam phasers, of the jack timing and things like that. And you see generally we can say there are a lot of activities going on in this field of turbocharging the gasoline engine. When we look back some years, we had a torque characteristic like this, but the negative side of former turbocharged gasoline engine was due to enrichment requirement. At full load, with higher speed, they had really excessive enrichment requirement. And to a wide extent, I do not know your opinion, but to a very wide public extent, the awareness, the image of the turbocharged gasoline engine to a wide extent still is that they are gas guzzler. But this has changed significantly. And when you look to modern and today's turbocharged gasoline engine, you see even the torque has raised significantly. On the other hand, the specific fuel consumption is absolute not moderate. So no excessive fuel enrichment anymore. So you really can say even the high performance turbocharged gasoline engines are very economic from a fuel consumption standpoint. This, of course, by means of cooled exhaust manifold like Audi does, cooled EGR and many other things, but basically it's the refined combustion which brought up this benefit. If you ask me for ideal chem timing strategy of a future turbocharged gasoline engine. It's only to visualize. We would like to have cam shifting on the exhaust side, to have appropriate scavenging, intake valve lift would give us the advantage to run Miller cycle, and of course we need the higher lift to utilize the performance which the clients are expecting. What will be the future of that kind of future turbocharged gasoline engines? This is the situation we have today. So the sweet spot is still of small size, and by whatever driving and transmission strategies we try to somewhere be inside of this area, but the combustion refinement will last on in the next year. We will have a situation like this. So the sweet spot is extremely widened up. Even the full load fuel consumption is reduced to, let me say, to a minimum, and such a wide sweet spot, of course, gives us much more possibilities from the drive. And if you look to modern transmission systems of today, you've heard it's not more enough to have 6-speed, 7-speed, it has to be 8-speed, and people are speaking of 10-speed automatic transmission. This all reflects because you want to set always your operation point somewhere into this sweet spot. So you see the contractions are, and of course it's easy to understand. The smaller is the sweet spot, the more different transmission ratios you have to utilize to catch this small bubble somewhere. But if we look to the future, if we consider a situation that the sweet spot is significantly enlarged, then with a 7-speed transmission, probably we will over-fulfill this target to a certain extent. We may, you see here is the road curve. But anyway, we may consider to go 1, 2, 3 steps back, and maybe 4-speed transmission will be sufficient, even to run economically in standard operation. And then, so it's far apart from variable valve train, we can bring one more component into the game. This is the electronic. Because here the combustion engineers do not have any solution. The operation condition of high efficiency to recharge the battery. This probably is the dream of automotive engineers, and probably this will improve the situation. Coming to the last example, is as I already mentioned, CSI engine, compression and spark ignition. This is hardcore. HCCI, this is definitely hardcore. So you can play around, but of course you can do a very professional job on it. Our belief is for HCCI combustion, you definitely need one flexible parameter where that you can adjust cycle-wise, preferably some element in the valve train. So we have proved this only for the sake of completeness. ABL played around with all the different kinds of direct acting variable valve lifting systems, and we have played around much with electromagnetic system, with the electro-hydraulic system and things like that. As a as a general standpoint here before I come to the HCCI, you expect to de-throttle the engine. This is one expectation. You want to control, you want to keep everything under control. But please bear in mind, the very important thing is here. It's the on-cost, and it's the power consumption of such a system. Because this does not help if you have a very sophisticated system, if the energy demand for this valve actuation system is high. I do not say the level. If this high deteriorates and this kills all your advantages, you are able to gain with such a system. So be very, very careful with the power requirement, and not to forget the safety, especially for electrohydraulic, so for the camless system. You have to make absolute sure that the valve always knows when to close. Usually this is the phase when the piston arrives. This you have to prove, this you have to make sure. One event of not controlling this behavior is the end of the engine problem. So safety, of course, is very important. So, I do it quick. This control compression and spark ignition engine. Basically, it consists of standard components. This is not something high sophisticated. It's only the combination, of course, which is probably more sophisticated. We still have a spark plug in the cylinder. We have gasoline direct injection. We have the standard chem phaser. The switchable habit we use is the same as Porsche uses. And the specific thing probably is this electrohydraulic valve actuation habit. This element with a control valve, we need to actively reopen the exhaust valve only for a small lift to repress exhaust gas from the exhaust duct, but this element has to be absolute, quick and accurate. With such an element, we have to control the charge cycle-wise. So to wait, to ramp up over several cycles probably is not sufficient. So you really, this is the need to control cycle by cycle. This is the precondition. Otherwise, all these HCCI systems will suffer from the deficit. And additionally, we have applied a piston, appropriate piston shape, to even be able to run stratified clean operation in idle mode. This is only an additional feature. Just shortly introduce you how the operating strategy looks like. In the high load area, we still run this engine stoichiometric number 1. Here in the higher hard load area, we're utilizing to run the engine stoichiometric number 1 with a very high degree of recirculated gas. You see, we run this here with this small lift, and this is the core area of our interest, where we are able to run HCCI combustion with the air-fuel ratio bigger than 1. That means lean combustion, but the aim of HCCI is to run lean, but without producing NOx. This is the aim of HCCI. And in that case, you see we're running the small intake lift. We still have the full exhaust valve lift, but what you see here, this is the reopening of the exhaust valve. So by this electrohydraulic solid, we are able to open and repress exhaust gas from the exhaust, which gives us the possibility to control the energy level of the charge, which at the end promotes to have HCCI combustion. And as I said, in idle mode, we are also able to run the The main challenge of HCCI combustion is not to keep the combustion stable. The big challenge is to transfer from HCCI combustion, this is somewhere controlled, controlled knocking, to normal spark ignition operation. And in that transient phase, you may have very hard cylinder pressure rise activities. And no driver would accept if you run from very smooth operation into some excessive noisy operation. The people would be surprised and frightened and things like that. So you have to run this transient always in a very controlled mode, so that the driver is not able to recognize whether you run with the spark ignition or you run on HCCI. This is a matter of controls, electronic controls, and on the other hand, as I mentioned, you need to have one feature to controlling the load exchange, and preferably this is one thing is in the water plane. I go into the final line. So, thank you. You're still very efficient, very interesting. How do we see the progress in this wide field of variable valve actuation? So a similar picture we already have seen. So for the gasoline engine, especially for the gasoline engine, we will have a very wide diversity of different technology. I do not want to read it now. Complementary to this, we also have we have to reduce friction. We have to have an appropriate thermal and energy management. We do not have to miss any opportunity. We really have to draw all the lines to make the system perfect. And in the future, we will see energy recovery system, hybridization, so the electrification will become more and more active. And again, the vehicles have to be affordable. And therefore, we always, whatever we do in the industry, we have to balance cost and value very precisely. Of course, we have the target to fight down the CO2 emission, but it must be affordable, and we are not allowed to do whatever we like or what we are able to do. We have to do what at the end the client is able to buy and afford. And out from these various technologies, I would like to draw an outlook. How does AVL see the status and also the penetration of new technologies? You see here the technologies, and I have split down it to different engine categories. So the very small engines having 1 liter, the next generation, so for B-class, C-class, up to 1.5 liter, then medium passenger cars, 1.4 up to 2.4 liter. 2.4 liter is quite very popular in the United States, so this 2.4 liter is the entry class in the United States. And even some light duty vehicle applications may come into the game. The trend analysis, I think, is easy to be understood. Starting with the chem phases, as I already showed you in the initial slides, this will become a standard, and especially for the bigger vehicle. We have 100% saturation of chem phases to this big, and it's moving down to the smaller engine. In Japan, it already happened, but Europe and Asian markets will follow. This is, I think, no doubt. The variable valve lift, so stepped movement. We see a very strong trend, especially in this area, and also in the smaller engines. This has arisen. But definitely this will in the fully variable valve training system. I have to look to Adrian. I see this less with less enthusiasm, because it's BMW, and the same as the Prince engine, Nissan, Toyota have such a system. They did an excellent job, but the question is, I heard it today, why does no one other copy this system? Whether it's an effect of marketing image or whatever, but this is always a good question. Why does no one else copy the system? But again, the BMW electronic system is, they have proved it, they have refined it, absolute perfect system. The system here in the very small engine, this is, let me say, currently an exception. This is the two-cylinder Fiat engine. We will see how this proceeds. Cylinder deactivation has been available in the past, will have a very strong renaissance. So starting from big engines, going to smaller engines, and as I already mentioned, also in very small engines, VW already has introduced, this will follow up. For the homogeneous GDI engines, some years ago we thought this naturally aspirated GDI will fade out, but from an image perspective, this technology is still quite very attractive in the higher classes, but the main trend is definitely turbocharging in combination with GDI. For the smaller engines, we will see probably more turbocharging in MPI. Cost-wise, very attractive solution. We will see for the GDI stratified as well as the HCCI. We have to put a question mark on it. So currently, nobody is able to forecast how this will happen. But you see, out of this big portfolio, a lot of opportunities, and we try to work on. If you ask what is the benefit I'm able to gain, when we look to former baseline, so this was the standard 4-valve MPI engine somewhere to 2 liter. All the technologies prove to have quite significant improvement potential, but time has moved. Currently, the turbocharged engine is the baseline of today, which we have to compare. And you see, all the other technologies in that combination are only able to contribute a much smaller portion as a benefit. We have to be aware of this. So you cannot add arithmetically add the contribution. You always have to do it by multiplication. GDI stratified here in this combination still looks quite promising, but as I told you, we see combination with Miller cycle, high EGR, so also mainly influenced from the valve grid. We think that this technology is very, very competitive, and high EGR systems in Miller have the very big advantages. They run stoichiometric lambda 1 and do not need a sophisticated exhaust after treatment for the exhaust gas. The conclusion, I do not want to read through. I hope you got the messages I want to give to you. You can read it in the handouts. And really, thank you very much for your patience and your time.
Thank you as well. And certainly, if there are some questions, please do not hesitate. Myself, I have a lot of questions, but I will write you an email. Anyway, are there any questions, please?
Yes. Earlier, when you mentioned that the fuel deactivation, cylinder deactivation brings a benefit of 4%, somewhere about. How much it compares to full deactivation of cylinders?
As a rough guess, I would say with simply electronic, you can grab two-thirds of the full potential, roughly. Yeah. Of course, if you completely shut the valve, this is definitely the ultimate solution. But by the simple thing, I would say at least you are able to grab two-thirds of the full potential. Not all, but it's a beginning. I have to add one more comment. So my presentation took quite exceptionally long, but I committed to Adrian because the last presentation was cancelled due to incident. So I already announced to Adrian that I allowed myself to really take the comprehensive collection of papers. So again, thank you for your patience.
Thank you. I need to say that apparently I have a problem. I'm wondering which one of you will still stay to hear my presentation, my last one. I will see, but before my presentation, let me invite you to have a cup of tea or a cup of coffee. So 15 minutes of break. Let's say more than 20 minutes. I want to talk. During the presentations of my colleagues, I thought that the guys or the men or the women that are working within the engine field must be some obsessed with control. We all understand under the current energetic context, the engine must become the more and more controlled. I don't know why the mankind, the people, have chosen the internal combustion engine instead of the electric motor. And I am a guy that works within this field since quite a while, but analyzing the electric motor, we all can understand the simplicity. But I suppose we all know the answer. Anyway, let's proceed with my presentation. As you see, it's about presenting some results obtained at my university in close cooperation with the Conservatoire National des Arts et Métiers de Paris. Here is the planning of my presentation. After a brief introduction, I will talk about I will present you some experimental results, as well as results issued from CFD simulation, and I will end with some conclusions. About the introduction, what can I say? I can repeat what everybody else already told. but it's my opinion as well that in spite of the things I said earlier, the internal combustion engine will still remain the main energy source for ensuring road mobility. This, in spite of its problem, it has a problem related with its negative impact on the environment. And we all know the greenhouse effect is a common topic nowadays. Therefore, European Union issued a regulation in 2009, no more than 130 grams per kilometer by 2015, no more than 95 grams by 2020. But what if the car manufacturer doesn't fulfill this requirement? We all talked about this, and I think we need to answer this question. As you see, it's about compensation payment, or should I say penalties. For instance, for each extra gram of CO2, the car manufacturer needs to pay €5. Then the algorithm is well presented on the slide. So in the end, we all understand it's about money. So a question about money, about millions of euros. So a question arises: what has to be done? Certainly, it's about improving the overall engine efficiency. Easy to say, hard to do it, isn't it? So as my fellow colleagues talked, here is the engine operation area during the new European driving cycle. And this is the difficulty. As most of its life, a passenger car is run under low loads and speed, where the overall efficiency decreases from the already not very high peak values to dramatically lower values, sometimes even below 10%. Variable valve actuation could be one of the answers, but as we all heard this day. According to Frost and Sullivan analysis, variable valve actuation can bring about 6% improvement in fuel efficiency with a cost of $425. It's my opinion as well, and I think we all agree, variable valve actuation itself cannot help us to achieve the CO2 target. So we have seen the presentations. Stefan discussed about the synergy with turbocharging, and the other colleagues as well. So there is not a unique answer. We need to combine these technologies. But in the end, it's about a trade-off between the cost and the performance. In the introduction chapter, these are the engine prototypes that we have in our lab. As you can see, it's about a mechanism that relies on a oscillating follower and a translational skate. The translational skate, the skate translates on the oscillating follower thanks to an assembly consisting in a connecting rod and a controlled lever. We have these two prototypes in our lab. It's a side-mounted camshaft with overhead valves and overhead camshaft. Both of them are operational, and I think we can see some experimental results. It's maybe the time to outline the fact that our research on this topic was possible thanks to the technical assistance of Renault Technologie Romani, who provided us with material for engine calibration and certainly with the know-how. Here you have the technical specification of our engine. You can see here for the two extreme cases that we approached, minimum intake valve flow H-min, maximum intake valve flow H-max, you can see the maximum valve lift and the valve timing. A graphical illustration of this table is presented here. So what we wanted to see was the positive F effects, if any, and there was, of operating at idle in stoichiometric condition with minimum intake valve flow. Here we have the measured intake valve loss. To serve this purpose, here is the instrumentation of our engine. I won't insist much about this, only to tell you that in red you can see the engine calibration system, and in blue you can see we monitor the in-cylinder and the instantaneous in-cylinder intake and exhaust manifold pressures. Certainly we wanted to have an idea about the normal flows, the back flows, or the reverse flows, and as you'll see, we concluded that employing the minimum intake valve lift will help us in this regard as well, as we approach idle operation. So if you ask yourselves what's the novelty of my presentation, nobody talked until now amongst you about idle. Certainly idle is perhaps not so not that interesting, but if we remember the congested city traffic, whether it is Pitești, not that much, but Bucharest or Paris or some other town, we can understand the importance of idle. And we talked, I asked you, Edward, about stop and start, and at that time with my colleagues we succeeded to have a stable idle operation at around 470 RPM. We thought, why not sleep and start rather than stop and start? Certainly there are some technical issues, but it appeared to us a bit important at that time. So about our experiments, let me describe the test procedure that we had. So first, we performed an ignition advance sweeping in order to find the best ignition advance for the particular case approached. So I remember we wanted to see the positive effect of using the H-min. So we can see for 30 crank angle degrees, here we obtain an 18.2% improvement in fuel consumption when using minimum intake valve flow. And concerning the cycle-to-cycle variability, which was studied by the coefficient of variance applied to indicated mean effective pressure, we observed a significant improvement. So we have chosen 30 crank angle degrees as the reference situation for the study, for the comparison that we made. Here we compare this value for spark advance, we compare H-min in blue, H-max in red. So what can we see? First, a higher peak pressure for the minimum intake intake valve law, and it can be explained by a higher effective compression ratio as the intake valve law, closing is earlier with the minimum low. Our calculations revealed an 8.1 for H-min and 5.8 for H-max. Remember, the geometrical compression ratio of our engine was 9. So let's take a look on this value. We can imagine the backflow that we have here, and we will see it. Another explanation of the higher peak pressure is the higher rate of heat release, as we can see here. And a consequence of higher heat release rate is an earlier end of combustion, as we can see here. These results can be attributed to the cumulative effects of these 2 points. An increased intake flow velocity, which causes an increased turbulence, which in its turn improves the fuel-air mixing process. And as expected, a lowering amount of residual burnt gas is a consequence of a lower internal EGR intensity. So as we saw, these 2 factors led to a better and more repeatable combustion. But in order to have a more clear idea about the flows from the manifold to cylinder, or from the cylinder to the manifold, we decided to launch a CFD study. It's maybe the time to tell you that up to here we have done all this research. Certainly, it's not. I didn't present everything within a PhD thesis, and my PhD student, let's say, or my good friend Adrian Buziak is here with me. So, and the CFD study was the second PhD thesis that we conducted on this subject, and it was a co-tutelage thesis with le Conservatoire National des Arts et Métiers. And my PhD student is here with us, Victor Yorga. I thank them both for their implication. So let's see the CFD simulation and the results. Here you can see the geometry, the meshing, and you can see the airflow is driven entirely by the motion of the piston valves. This is why we call this simulation as a dynamic one. And the turbulence model chosen was the K-epsilon realizable. Certainly we needed to validate our CFD model, and for this purpose we, as you can see here, it was about simulating the motor engine at 800 RPM for 20.8 degrees throttle opening for the 2 situations, H-min, respectively H-max. And as you can see, here we have the in-cylinder pressure evolutions, and as you can see, in H-max, as well as in H-min, there is a pretty good concordance between the experiment and the simulation. So the conclusion was we can consider this CFD simulation as trustworthy. We were interested in exact figures about maximum flow velocity in the intake valve gap. So as expected, in H-min we obtained a pretty high velocity, 160 meters per second, while in H-max situation we barely obtained 32 meters per second. So these results support the conclusions that I was talking about earlier. let's take a look on the evolution of in-cylinder air mass. And I would like you to focus your attention on the downward evolutions, whether they are here or they are here. Here is the beginning of the intake process, intake valve opening for HMAX, and we can see a reverse flow from the cylinder to the intake and exhaust manifold. At the end of the intake process, we can see again a backflow. This backflow doesn't exist for HME, as we cannot see a downward evolution, and here we have a downward evolution, but taking into account that the intake valve opening occurs here, then we can conclude the backflow is toward the exhaust manifold. What we can see here is that, however, the filling efficiency in the case of the HMAX is better. So the positive effect of restraining the intake valve flow related with the intensification of flow velocity is, let's say, diminished by this volumetric efficiency, which is lower. So one option would be to easily extend a little bit the intake valve flow in order to have the same filling efficiency as in the HMAX situation. And the explanation of this difference is expected in the greater pumping work for HME case, as you see here. So certainly we are all looking for improving the internal aerodynamics of the engine, but apparently a compromise should be done between internal aerodynamics, pumping and filling efficiency. And here it's maybe the time to tell you, my fellow colleagues talked about BMW's Valvetronic. In order to achieve the throttless control, engine load control, they use the strategy variable intake valve flow coupled with varying the intake valve closure. The intake valve will close earlier as the load goes down. But in the case of idle operation, BMW switches the strategy, because at idle operation they don't, by using the EIVC strategy, they don't have enough internal aerodynamics. After the moment of the intake valve closing, there is an expansion during the rest of the intake stroke, and all the mixture is quite calm, let's say. It's quite calm. So the strategy they chose for idle operation, apparently after what I've been reading since quite a while, is late intake valve opening. So they are opening the intake valve pretty late, and the moment the valve is open, the vacuum being intense, the flow velocity is what is important. So you see, internal aerodynamic is important. I don't need to tell you this, you all know that. But BMW, by using this strategy, LIVO, late intake valve opening, they are losing the pumping side. So the engine is piping quite higher, even though it doesn't have a throttle, but apparently it is more important for BMW that at idle to have enough internal aerodynamics. So it might be idle operation. It might be not regarded as important, but believe me, it is important. And one important thing in this particular operating point is the probability ensuring a stable idle operation. All right. When talking about internal aerodynamic, we should take into consideration large-scale movements as well. Since the design of our combustion chamber is not suited for tumble motion, we explored only the swirl motion. We calculated, using the information from Fluent ANSYS, we calculated the swirl number, and as you can all see, there is an obvious improvement in the case of H-mean. And here we have the fluid particles trajectories. And we can see the trajectories described by the particles are longer at H-mean. And we have certainly chosen the same number of particles. Why? Because as a result of the intensification of the swirl motion. And as you can see, we only have 3 slides. Here there are some, this is the last slide from this chapter, and we can see the turbulent kinetic energy and the intensity of turbulence in some important moments of the cycle. In a chronological manner, it's about the moment of reaching the maximum flow velocity at the intake valve gap, the intake maximum valve lift, the end of intake stroke, or the bottom dead center, the intake bottom dead center, and the end of compression stroke, the compression top dead center. What can we see here? An obvious improvement in the internal aerodynamic of the engine, but in spite of our efforts, we can see at the end of compression stroke, we barely notice a difference. So it's my opinion that when we are seeking to have internal aerodynamics, we should have it even at the end of compression stroke, in order to have a faster combustion, thus better efficiency. Why we have obtained this, I cannot tell you. We ran out of options, and we told ourselves we need to finish the thesis. So we ended without providing some, but I will talk with my colleagues this evening. Maybe we can find an answer. About the conclusions, I will not talk about conclusions related with this particular study. I wanted to make a brief presentation of what we have been doing here at my university since quite a while, 2005, as I said in the morning. But you can imagine, everybody, that it's a pretty much difference between a university and an industrial society, let's say. We are 4 people, 4 men that are working, including my technician who will retire this fall. So this was a brief presentation, and the conclusions is rather general. So we believe in a more than a century of internal combustion engine evolution, of gasoline engine evolution, the advances that we noticed, it's pretty much caused by the automatization of ignition and air-fuel ratio. In other words, with ignition and injection, which they have become, let's say, like state-of-the-art technique. Nothing is left to the hazard. Everything is controlled. That's why I think I told you a bit earlier, the guys who are working in this field are perhaps control freaks, a bit obsessed with control. So variable valve actuation, together with the other techniques that we all heard about, can bring its contribution in order to achieve the fuel economy that we all want, and in order to achieve the pollution reduction. So this is it. Thank you for being today with us, and certainly if you have some questions, do not hesitate.
One question, please. Have you estimated the flow coefficient?
No, we haven't. I've seen at the Edwards presentation swarm number and flow coefficient as well. And I figured myself that perhaps I will be asked about this. No, we don't have neither the means experimentally.
I asked just friendly.
I know. No question about it. Thank you all for being here today. I will send you by email all the presentation in PDF format. My colleagues authorized me to send you all the presentation. I will send you all their email addresses, and I think they will be happy to answer you by email to all your questions. It's not easy to talk in English. Yesterday I was telling to my friend Pierre, I have had enough of English and French. I would like to talk in Romanian. And if somebody forgets to leave his or her email address, please write it down so I can send the presentation to you. I won't tell anything else then. Thank you so much.
Thank you.